It's September 1859, and in Havana, Cuba, people are looking up at the night sky in confusion, because there, hanging above the palm trees, is an aurora. Not a rumour of one, not something you'd need to travel to Norway to see. A full-blown curtain of fire, red and green aurora, glowing right above a tropical city, thousands of miles from where it should be. And Cuba wasn't alone. People in Hawaii saw it. People in Colombia saw it. Gold miners in the Rocky Mountains woke up in the middle of the night, saw the sky glowing bright enough to read a newspaper by, and started cooking breakfast because they genuinely thought the sun was rising. It wasn't. It was 1 a.m. Meanwhile, thousands of miles away, telegraph operators were sitting at their machines watching something that should have been impossible. Sparks jumping off the wires, operators getting shocked just for touching their equipment, and in some cases messages being sent, actual working telegraph messages with the batteries completely disconnected. The system was running on something else entirely. Something coming from space. This was the Carrington Event, and it remains to this day the most powerful solar storm ever recorded in human history. But here's the question that should be keeping you up tonight. What did it actually do back then? Not the exaggerated version. Not the doomsday version you've probably seen in some YouTube thumbnail with a fireball hitting the Earth. What really happened in 1859? And maybe more importantly, what would happen if a storm exactly that strong hit us today? In a world running on satellites, GPS, the internet, and a power grid so interconnected that one failure in one state can black out an entire region in minutes. That's what we're going to figure out together. Real evidence, real eyewitness accounts, real scientific reconstruction of an event that happened before anyone had a way to properly measure it. But before we go there, if you're listening to this while trying to fall asleep, tell me where you are and what time it is right now. I love checking the comments and seeing this insane spread. Someone in Manila at sunrise, someone in Chicago at midnight, someone in London on their lunch break, all listening to the same story at completely different moments. It's a strange kind of company, and I want to know who's out there with me. And if you'd rather listen without ads, without music breaks interrupting the story, Spotify has you covered. Just search for the show, hit follow, and you'll get the clean, ad-free, music-free version every time. There's a link in the description if you want to jump straight there. And if you're already there and enjoying these, a 5-star review genuinely helps more than you'd think. It's basically the only way people find these stories. Okay, back to 1859. Here's what we're actually going to do in this one. We're going to start with the world as it existed right before the storm, a world just barely wired together by telegraph lines, fragile and new. Then we're going to meet the man who watched it happen through a telescope in real time, an amateur astronomer who saw something on the sun that no one had ever documented before. From there we'll dig into what scientists now believe was actually happening on the sun itself. The sunspots, the magnetic tangles, the explosive release of energy that sent a wave of charged particles racing toward Earth at speeds that still seem almost unbelievable. And once we've laid out exactly what happened in 1859, we're going to drag this story into the present. Because the sun hasn't changed. It's still capable of producing a storm just as strong or stronger. The only thing that's changed is us. And that's where things get genuinely unsettling. To understand why the Carrington event hit the way it did, you have to understand what the world actually looked like in the summer of 1859. And I mean really looked like, because it's easy to picture the 1850s as some kind of pre-technological dark age. Horses, candles, people writing letters that take 3 months to arrive. That's not quite right. Something extraordinary had just happened, something that made 1859 fundamentally different from any year that came before it. For the first time in human history, information could travel faster than a person could physically move. The telegraph had been around for about 15 years at this point, and in that time it had exploded across the industrialized world with a speed that genuinely rivals how fast the internet spread in the 1990s. By 1859, there were tens of thousands of miles of telegraph wire strung across North America and Europe. Iron wires held up on wooden poles running along railroad lines, stretching across farmland, crossing rivers, connecting cities that used to feel like they existed in separate worlds. A message that once took weeks to travel from New York to Chicago could now arrive in minutes. Stock prices, news, personal messages, military orders, all of it was suddenly moving at what felt like the speed of thought. This was the internet of the 1850s, not in some loose metaphorical sense, but functionally. It was the system that connected commerce, government, and daily life across vast distances. Newspapers reprinted telegraph dispatches from other cities as breaking news. Businesses coordinated shipments and prices across state lines. Railroads depended on telegraph signals to keep trains from colliding on shared tracks. An entire economic and social structure had rapidly reorganized itself around the assumption that instant long-distance communication now existed. And just like the internet today, almost nobody using it fully understood how fragile the underlying technology actually was. Here's how it worked, and this detail matters a lot for what happens later in this story. Telegraph systems ran on direct current electricity, produced by batteries, usually simple wet cell batteries, filled with chemical solutions that needed regular maintenance. This current travelled down a single wire to a receiving station, where it triggered a clicking mechanism that operators had trained themselves to read like a language. But here's the part that made the whole system vulnerable in a way nobody anticipated. Most telegraph lines used something called a ground return. Instead of running two wires, one to carry the current out and one to bring it back, engineers saved money and materials by using a single wire and then completing the electrical circuit through the earth itself. Metal rods driven into the ground at each station served as the return path. The earth itself was part of the circuit. This was clever engineering for its time. It cut costs roughly in half, but it also meant that these lines, sometimes running for hundreds of miles in a nearly straight path, were essentially enormous antennas laid directly into the ground, completing loops of exposed wire and earth across the countryside. Nobody in 1859 thought of them that way, because nobody in 1859 knew that the ground itself could carry unexpected electrical currents from a source 93 million miles away. That idea would have sounded like science fiction. Actually, it would have sounded like nonsense, because the concept didn't exist yet. Which brings us to the second thing you need to understand about 1859. The term space weather didn't exist. Nobody used it, nobody thought in those terms because the sun was not yet understood as a source of anything that could physically reach and affect the Earth. People had been seeing auroras for as long as there were people to see them. Ancient cultures had myths about the northern lights, spirits dancing, dragons breathing fire across the sky, omens of war or death. By the 1850s, educated observers knew auroras tended to appear more often near the poles, and they'd noticed some vague correlation with sunspot activity, but the actual mechanism was a complete mystery. Nobody knew that the sun could fling billions of tons of magnetized plasma into space. Nobody knew Earth had a magnetic field that could be disturbed by anything, let alone something arriving from beyond the atmosphere. The very idea that events happening on a burning ball of gas 93 million miles away could directly cause sparks to jump off a telegraph wire in Boston would have struck most scientists of the era as absurd. Electricity itself was still a relatively new and somewhat magical force in public understanding. It had barely been harnessed for practical use, telegraphs being basically the only widespread application. So when strange things started happening with electrical equipment, There was no existing framework for understanding it. This is important because it's exactly why a solar storm's first noticeable fingerprint on human civilization wouldn't be some dramatic explosion or fireball. It would be something much stranger and, in its own way, much creepier. Weird currents showing up in long wires. Currents that shouldn't be there. Currents nobody sent. Long wires laid across the landscape, especially those running roughly north to south, following certain geographic and geomagnetic alignments, are essentially perfect instruments for detecting disturbances in Earth's magnetic field. When that magnetic field gets violently shaken by an incoming blast of solar particles, it induces electrical currents in any sufficiently long conductor nearby. Telegraph wires, with their hundreds of miles of exposed metal and their ground return circuits, were about as perfectly designed for this kind of accidental detection as anything humans had built up to that point. So when the storm hit, the first place ordinary people would notice something was deeply wrong wasn't the sky. It was the telegraph office, and this is where the stakes of this story really start to take shape. In 1859, dependence on interconnected technology was real, but it was narrow. Telegraph lines mattered enormously for commerce, news, and military coordination. But if every telegraph line on the continent went down simultaneously, society did not collapse. People still had horses, mail carried by train, local economies that could function without instant communication. It would have been a disruption, a costly and strange one, but not a catastrophe. Compare that to now, where a solar storm capable of the same intensity would be hitting a planet wired together by power grids, satellites, GPS timing signals, and an internet infrastructure that underpins literally everything from banking to hospitals to water treatment. That comparison is the entire reason this story from 1859 still matters today. One more detail worth noting. Because telegraph infrastructure was heavily concentrated in Europe and North America at this time, that's also where almost all of the detailed reports of the storm's effects come from. Regions with dense wire networks generated dense evidence. Places without that infrastructure may have experienced identical solar effects overhead, but they simply left far fewer written records behind. That's an important thing to keep in mind as we move forward, because it shapes exactly what history remembers about this event and what it doesn't. So that's the world right before the storm, wired together for the first time, utterly unaware of what the sun was capable of, and about to get a very rude introduction. Which brings us to the man who was actually watching the sun that morning, and who would end up giving this entire event his name. Richard Carrington was not a mad scientist staring at the sun through some improvised death telescope. He was a meticulous, almost obsessive observer, doing exactly what serious astronomers of his time did: watch sunspots. Day after day, hour after hour, carefully, methodically, like a bookkeeper auditing the surface of a star. By 1859, Carrington was in his early 30s, running a private observatory on his family's estate in Redhill, south of London. He wasn't some random amateur. He was already known in scientific circles for very precise work on sunspots and solar rotation. This is important, because what he was about to report was so weird that if it had come from anyone less careful, it might have been dismissed entirely. His daily routine was simple in concept and demanding in practice. On clear mornings, he'd aim his telescope at the sun and project the image onto a white screen so he could trace the spots without frying his own retinas. No heroics, no staring directly at the solar disk, just careful projection and drawing. He'd mark the positions, track how they drifted across the sun, estimate their sizes, day after day, building up the data set that would let him map how fast different parts of the sun rotate. On the morning of September 1st, 1859, he started out doing exactly that. The sun had a particularly large, complex group of spots crossing its face, the kind of structure any solar observer would pay attention to. Around 11:18 in the morning local time, while he was sketching, something happened that was so out of the ordinary that it broke his own workflow mid-line. Carrington later described it in language that, for a Victorian scientist, counts as holy crap. He saw within that sunspot group 2 intensely bright patches of light suddenly appear, almost side by side. He compared them to 2 patches of intensely bright and white light superimposed on the dark spots, so bright that they stood out even against the projected image of the sun's glare. They didn't just wink on and vanish, he watched them. For about 5 minutes, he saw these brilliant regions move, almost like they were sliding across the sunspot group, then gradually fade. He was so startled that he briefly left the room to fetch a witness, another worker on the property, but by the time they got back, the flare was already diminishing. The brightest, most dramatic phase had passed. He had caught it. No one else there had. What Carrington had seen is what we now call a white light flare. That phrase sounds tame, almost boring, but in solar physics it marks something extreme. Most solar flares are best seen in specific wavelengths: X-rays, ultraviolet, hydrogen alpha light. Today we detect them with instruments and filters that isolate those bands. To the naked eye, or to a simple visible light projection like Carrington was using, most flares don't stand out dramatically against the already blinding photosphere of the sun. For a flare to show up as brighter than normal in plain visible light, it has to be extraordinarily energetic. You're looking at a local eruption so intense that it boosts the visible continuum light of the solar surface itself. That's why white light flares are rare, or at least rarely reported by humans, using unfiltered, visible-only techniques. The sun is already very, very bright. Anything that makes part of it noticeably brighter to our eyes is doing something violent on a massive scale. Carrington, of course, had no modern vocabulary for this. He didn't know about X-ray flux or magnetic reconnection. He called it a singular appearance, an outburst, a sudden brightening, but he did exactly what good scientists are supposed to do when something unexpected happens. He wrote down everything: time, position on the solar disk, shape, motion, duration. He even went back to his drawing and carefully marked where the flare had been relative to the sunspots he'd been sketching. Later that same day, another British observer, Richard Hodgson, independently reported seeing a similar brilliant flash in the same general sunspot region. 2 independent accounts, both from experienced observers, describing something highly unusual. That dual confirmation is one of the reasons history takes this observation so seriously. Now, did Carrington watch that flare and instantly say, "Ah, yes, this will cause a geomagnetic superstorm that will wreck the telegraph system in a day and a half"? Absolutely not. That's one of the modern myths that needs to die. He had no framework to connect a solar outburst to terrestrial electricity. Nobody really did. As far as he knew in that moment, he had just witnessed a bizarre, possibly unique solar phenomenon. Interesting. Yes. Dangerous to Earth? No obvious reason to think so. The linkage between what he saw and what came next was only recognized after the fact, and even then, only in pieces. Within about 17 hours of his observation, Earth's magnetic field started going haywire. Telegraph systems began acting strange. Auroras would soon appear in places they had no business appearing. Over the days that followed, scientists and telegraph operators compared notes. A few people began to suspect that the timing was not a coincidence, that maybe, somehow, the sun and the geomagnetic disturbance were connected. Carrington himself cautiously raised the possibility. In a paper he published soon afterward, he pointed out the coincidence in time between his flare and the magnetic storm recorded by observatories on Earth. But he didn't claim he had proved causation. He couldn't. The physics simply didn't exist yet. He was proposing a link, not asserting a law of nature. His contemporaries were split. Some thought it was an intriguing correlation worth investigating. Others were sceptical. Victorian science was still wrestling with what the sun even was. A ball of burning coal, a glowing fluid. The idea that it could hurl something invisible across 93 million miles of space in less than a day and shake Earth's magnetism sounded speculative at best. For decades, Carrington's observation lived in that grey zone, notable, suggestive, but not fully integrated into a coherent theory. It was only later, with the development of plasma physics, the discovery of the solar wind, and the concept of coronal mass ejections, that scientists went back to Carrington's drawings and said, in effect, "Oh, that's what we're looking at." A massive flare, almost certainly associated with a violent ejection of solar plasma, launched directly along a line that intersected Earth. Even then, caution is warranted, we can't go back in time and film the sun. We infer, we model, we say things like, the 1859 event is consistent with what we'd expect from a powerful CME associated with a white light flare, but we can't replay the eruption. Carrington didn't see the CME itself. Nobody did. He saw one sudden flash in visible light, a footprint of the underlying magnetic explosion. What he did not do was stand in his observatory and predict global chaos. He didn't forecast telegraph failures. He didn't warn governments. He documented a key moment in a chain of events that nobody yet understood as a chain. The real historical significance of Carrington's observation is twofold. First, it gave us a precise timestamp and a solar location for the most intense geomagnetic storm on record. Second, it planted the seed of an idea that the sun is not just a distant lamp in the sky, but an active eruptive neighbour capable of reaching across space and touching the technology we build on Earth. At the time, that idea was radical. In hindsight, it seems obvious. But science is built on moments like this, where one careful person sees something strange, writes it down, and refuses to let the anomaly be forgotten. Carrington's flare was that moment. The sun had just thrown a punch. Humanity wouldn't realize how hard it had been hit until the weirdness started showing up, not in telescopes, but in telegraph offices around the world. To understand what actually happened on the sun that day, you have to zoom out from Carrington's drawing board and think about what a sunspot really is. On the surface it looks simple, just a dark blemish on an otherwise smooth disk, a cosmic freckle. But that freckle is the visible tip of a magnetic monster. The sun is a ball of plasma, not a solid object. Its equator rotates faster than its poles. Different layers slip past each other. All of that motion twists and stretches magnetic fields inside it like rubber bands in a blender. Where those tangled fields punch through the visible surface, they inhibit the flow of heat from below. The gas there cools slightly, from about 5,800 degrees Kelvin to maybe 4,000 or so. Against the surrounding glare, it looks dark by comparison, even though it would still outshine an arc furnace. So a sunspot isn't a cold hole. It's a sign that magnetic fields there are incredibly strong, thousands of times stronger than Earth's field at the surface. And those fields are under stress. They're bent, sheared, knotted. All that distortion stores energy, the same way bending a spring stores potential energy. The more complex and twisted the magnetic structure, the more energy it can suddenly release if something snaps. Carrington's particularly large, complex group of spots was one of these stressed-out regions. Today we'd call it an active region. That's not just poetic language. In modern solar physics, an active region is a cluster of sunspots and magnetic fields that's actively evolving, reshaping itself. and, crucially, prone to eruptions. If you want big flares, you watch the big, messy active regions. Inside an active region, the magnetic field lines aren't calm loops. They cross, tangle, and sometimes get pushed together so tightly that the plasma in between can't keep them apart. When that happens, something dramatic can occur. Magnetic reconnection. Two bundles of field lines snap, reconfigure, and suddenly connect in a lower energy configuration. The difference in energy doesn't politely disappear. It blasts out in radiation and in accelerated particles. That sudden dump of magnetic energy is what we call a solar flare. A flare is, at its core, a burst of light and high-energy particles. X-rays, extreme ultraviolet, gamma rays in the most extreme cases. It's an electromagnetic flashbulb going off in the low solar atmosphere. The energy is released in seconds to minutes. In space weather terms, it's the light speed part of the event. The radiation rushes out at, effectively, the speed of light, hitting Earth's upper atmosphere about 8 minutes after it leaves the Sun. But a flare is not the same thing as a coronal mass ejection, a CME. That's a separate beast. A CME is when a huge bubble of the Sun's outer atmosphere, the corona, gets hurled into space. We're talking billions of tons of plasma, threaded with magnetic fields, launched outward at hundreds to thousands of kilometers per second. It's not just light, it's matter, a moving, structured magnetic cloud. Sometimes a big flare and a big CME happen together, like different aspects of the same underlying magnetic catastrophe. The flare marks where the energy is dumped as light and heat. The CME is the chunk of overlying magnetic structure that gets blown off as everything rearranges. Other times you can get a strong flare without much of a CME, or a CME with only a modest flare. The connection is real but not one-to-one. In 1859, nobody knew any of this vocabulary. They had spots and outbursts. That was it. From our vantage point, looking back with a century and a half of theory and spacecraft data, Carrington's white light flare almost certainly came from a magnetically complex active region that had built up a dangerous amount of stored energy. When it let go, it likely launched a CME, but for that eruption to matter to us, it had to be aimed the right way. The Sun is throwing off little puffs and jets all the time. Most of them miss Earth completely. Space is big, and our planet is a tiny target. For a CME to hit us, its trajectory has to intersect the narrow cone that contains Earth's orbit at that moment. The geometry is unforgiving. Now layer on the fact that Carrington's flare occurred in a sunspot group, roughly near the centre of the solar disk as seen from Earth. That's an important clue. Eruptions that originate near the visible centre of the Sun are more likely to be Earth-directed, because the magnetic structures above them are already pointed, roughly along the line between the Sun and Earth. Move that exact same active region to the limb, the edge of the disk, and the odds of a direct hit drop dramatically. The CME, if one occurs, tends to head off to the side. Timing matters too. The Sun rotates roughly once every 27 days as seen from Earth, carrying active regions across its face like continents rotating into and out of view. A region that's perfectly Earth-facing today will be rotated away in a week. There are windows where an active region is in a prime position to send material our way, and windows where it's essentially harmless from our perspective, even if it's still explosive locally. Modern observers watch these active regions rotate into view, flare repeatedly, and sometimes spit out chains of CMEs over days. Eruptions cluster. Once a region has built up the kind of magnetic stress that produced Carrington's flare, it doesn't usually calm down after one event. It's more like a fault zone after a big earthquake. Aftershocks, secondary slips, continued activity as the system relaxes. We know from 19th century magnetometer records that the storm on September 1–2, 1859 was not an isolated blip. There were geomagnetic disturbances in the days around it, and sunspot drawings from multiple observatories show that this was not a single lonely spot but a sprawling complex. In other words, the Sun was in an active mood, and that particular region was the troublemaker. How much of that can we say with confidence? Less than we'd like. We don't have satellite images of the 1859 Sun, no coronagraph movies showing a CME swelling and racing outward, no spacecraft parked upstream from Earth measuring the magnetic structure of the incoming cloud. All of that belongs to the late 20th and 21st centuries. What we do have are Carrington's and Hodgson's drawings and timings, sunspot sketches from other observatories, reports of unusually large spots visible even to safe naked eye observers through smoke or haze, and the magnetic and telegraph disturbances that followed. We can feed those constraints into modern models and ask, if we saw this set of effects today, what kind of solar eruption would we infer? The answer points strongly toward a fast, massive CME launched from an Earth-facing active region, probably tied to the white light flare Carrington saw. But there are still debates in the literature. Was the storm that hit on September 2nd associated with Carrington's flare itself, or with an earlier eruption from the same region whose CME preconditioned space around Earth? Were there multiple CMEs in quick succession piling on to create an especially intense impact? Did the geometry line up in an unusually efficient way, with the CME's embedded magnetic field oriented just wrong for Earth's defences? We can't resolve all of that from mid-19th century data. We can outline plausible scenarios, rule out the ones that don't fit the timing or the strength of the storm and say, with reasonable but not absolute confidence, that a violently active magnetic region on the Sun threw a major eruption almost straight at us. From Carrington's perspective, that active region was just a complicated patch of darkness. From ours, it was a coiled magnetic weapon, storing energy over days and then releasing it in a form that could cross 93 million miles and rattle the technology of an entire planet. What left the Sun that day, though, wasn't just light. It was a physical blast wave of plasma and magnetic field racing outward through the solar system. And it made the trip from there to here much faster than you might guess from a casual look at a textbook diagram of the orbits. 93 million miles sounds like a lot. In everyday terms, it's obscene. At highway speeds, it would take over 100 years to drive from the Sun to Earth. Even a bullet would need months. So how does a solar storm made of actual matter cross that gulf in less than 2 days? To get there, you have to stop thinking of space as empty. The Sun is constantly bleeding, not in chunks like a CME, but as a steady ghostly outflow of plasma we call the solar wind. Every second, particles leak from the corona and stream outward in all directions, carrying the Sun's magnetic field with them. By the time that wind reaches Earth, it's thinned out to a whisper, but it never stops blowing. Our entire solar system is immersed in it. In that wind, a CME is not a lone cannonball flying through a vacuum. It's more like a dense, magnetized storm front ploughing through an already moving air mass. When the coronal mass ejection leaves the Sun, it doesn't start from zero. It erupts into a solar wind that's already racing outward at hundreds of kilometers per second. The CME is a bubble of plasma threaded with its own internal magnetic field, expanding and driving through that background flow. Its outer edge can form a shock wave, like the bow wave in front of a ship. Typical CMEs, the kind the Sun throws off all the time, might travel at 400, 600, maybe 800 kilometers per second. They take 2, 3, 4 days to make the trip to Earth's orbit, if they happen to be pointed at us at all. That's the normal space weather rhythm. Eruption on day 1, geomagnetic storm 2 or 3 days later. The 1859 storm didn't follow that schedule. Carrington saw his flare late in the morning of September 1st, Greenwich time. By the evening of September 1st into the early hours of September 2nd, Earth's magnetic field was in chaos and telegraph lines were sparking. Depending on which timing you use, the delay between solar eruption and planetary impact looks more like 17 to 18 hours than several days. That's ridiculously fast for a CME to cover 150 million kilometers in less than a day. Its average speed has to be on the order of 2,000 to 3,000 kilometers per second, among the fastest ever inferred. Modern spacecraft have directly measured only a handful of events in that extreme category. The 2003 Halloween storms produced some. So did a notorious eruption on July 23, 2012, that missed Earth but slammed into a different spacecraft and set off alarm bells in the space weather community. So how do you get a plasma cloud to go that fast? Part of the answer is energy. The more magnetic energy is stored in the active region before it erupts, the more can be converted into kinetic energy of the CME. Stronger fields, more twisted configurations, bigger volumes of gas involved, all of that can drive higher speeds. But there's another subtler factor, what the CME has to push through. Think about ploughing a car through deep snow versus driving on a road someone else has already cleared. Same engine, same tyres, totally different experience. In space, snow is the slower, denser solar wind ahead of the eruption. If a previous CME from the same active region has blasted out along a similar path, it can effectively clear that road. It sweeps up and compresses the plasma ahead of it, leaving behind a region of lower density and altered magnetic structure. When the next eruption comes along, it finds less resistance. It can maintain a higher speed, maybe even accelerate, because it's not spending as much energy shoving slow wind out of the way. Space weather researchers call this preconditioning. It's one of the leading ideas for why some storms, including Carrington's, appear to have arrived absurdly quickly. We know from magnetometer data and sunspot records that late August and early September 1859 featured multiple disturbances, not just a single isolated blast. The stage may already have been set. There's also the role of driving fields, how hard the eruption itself is, pushing. A CME launched with an exceptionally strong internal magnetic field can, in effect, muscle its way through the surrounding wind more efficiently, sustaining very high speeds over long distances. Combine strong driving with a preconditioned path, and you get the kind of transit time that makes modern forecasters sweat. But even a record-breaking speed doesn't automatically translate into record-breaking damage. From Earth's point of view, what matters most is not just how fast the storm arrives, but how its embedded magnetic field is oriented when it gets here. Earth has its own magnetic field, roughly dipolar, north and south, like a bar magnet tilted a bit relative to our rotation axis. The incoming CME also carries a large-scale magnetic field, frozen into the plasma inside that cloud. When those two fields meet, their geometry determines how much energy can be transferred into Earth's magnetic environment. If the CME's field is oriented mostly northward when it hits us, aligned with Earth's north-pointing field on the day side, they tend to slide past each other like magnets with the same poles facing. There's interaction, some disturbance, but comparatively less efficient coupling. If the CME's field is strongly southward opposite to Earth's, that's a different story. Opposite polarities can reconnect. The boundary between the two magnetic systems becomes leaky. Energy from the solar storm pours into Earth's magnetosphere far more effectively. That's when you get the largest geomagnetic storms, the deepest current systems, the auroras pushed to tropical latitudes. Speed influences how suddenly that coupling begins and how intense the compression is at the front of the magnetosphere. Orientation controls how wide the door is once the storm starts knocking. The Carrington event seems to have been extreme on both counts. a very fast CME, likely carrying a magnetic field oriented in a way that was particularly bad for Earth's defences. But to see why that orientation matters so much, we have to look at those defences themselves. Because Earth is not just sitting there in the solar wind, naked and exposed. It's wrapped in its own invisible magnetic cocoon, a structure that takes the full brunt of a CME's arrival, distorts, strains, and sometimes cracks under the pressure. That cocoon, the magnetosphere, is the reason most solar storms pass by as pretty lights in the sky instead of civilization-ending catastrophes. Understanding what it does and how it can be overwhelmed is the next piece of the story. Imagine you could see magnetism, not just compass needles. The whole thing. Invisible lines of force arcing out of Earth's south polar region, looping around in great curtains and plunging back in near the north. A bubble stretched and squeezed by the constant pressure of the solar wind. That's the magnetosphere. It's not a physical shell you could bump into. It's a region of space where Earth's magnetic field dominates over the Sun's. Inside that region, charged particles mostly dance to Earth's tune. Outside, they're part of the solar wind. When the solar wind blows against this magnetic bubble, it doesn't slam straight into our atmosphere. Most of it flows around. The dayside field gets compressed into a blunt nose, maybe 10 Earth radii from the planet's centre. On the night side, it stretches out into a long magnetic tail that can reach hundreds of Earth radii downwind. That simple deflection is already a huge deal. Take away the magnetosphere and the solar wind would crash directly into our upper atmosphere all day, every day, eroding it over geological timescales the way it did to Mars. It would also drop high-energy particles across the entire dayside sky, not just the polar regions. You would not want to be running a technological civilization in that environment. So, in quiet times, the magnetosphere works like a cosmic breakwater. The stream of charged particles hits the field, gets diverted around it, and continues downstream. The vast majority of the solar wind never touches our air. But a CME doesn't just bring more particles, it brings organised magnetic structure. And when one big magnetic system slams into another, weird things happen. The key process here is something called magnetic reconnection. The name sounds abstract, but the basic idea is surprisingly intuitive. Picture two sets of magnetic field lines running in opposite directions, pressed together at a boundary. Field lines don't like to just sit there, perfectly opposed. Under the right conditions, they can break and swap partners, reconnecting in a different configuration. When they do, magnetic energy is converted into heat and motion of particles. It's like stretching rubber bands until they snap, and then watching them whip back into a new arrangement. At the front of Earth's magnetosphere, where the solar wind first encounters our field, reconnection acts like a gate. Most of the time that gate is mostly shut. Our field and the interplanetary field are arranged so they just shear past each other. The solar wind slides around the bubble. Only a trickle of particles and energy leak through. Flip the solar wind's magnetic field, and that changes. If the magnetic field embedded in the solar wind is pointed northward, roughly in the same direction as Earth's field on the dayside, opposite polarities don't touch. It's like trying to stick two bar magnets together, north to north. They repel. Reconnection is weak and patchy, energy transfer is limited. If the CME's field is strongly southward, now you've got north meeting south. This is the configuration that nature loves to reconnect. The magnetic fields at the boundary can merge efficiently, opening long-lived channels for plasma and energy to stream directly into the magnetosphere. Instead of a mostly closed door, you've got the hatch swung wide open. That's why space weather scientists obsess over southward biz when a CME is incoming. BZ is just the component of the magnetic field pointing north-south. Get a strong, sustained negative BZ southward, and you've got the perfect recipe for a big geomagnetic storm. The magnetosphere isn't just being punched, it's being plugged in. Once that gate opens, the system doesn't blow up all at once. It charges. Reconnected field lines on the day side get dragged backward by the solar wind into the magnetotail, that long streamer of night side magnetic field. Think of the tail as two sheets of field lines, one from the northern hemisphere, one from the southern, pulled taut and storing tension like a gigantic bowstring. As more and more flux is piled into the tail, magnetic energy accumulates. Charged particles get trapped and accelerated. The whole night-side region becomes a reservoir of stored energy, waiting for its own breaking point. Eventually it reaches it, deep in the tail. Another reconnection episode kicks off. Field lines snap and reconfigure, flinging particles back toward Earth along newly closed loops that dive into the polar upper atmosphere. This is a substorm, a sudden unloading of that stored energy. From the ground, you don't see reconnection, or field lines, or plasma sheets. You see the sky come alive. Those particles streaming down magnetic field lines collide with atoms and molecules high above the surface. Oxygen glows green and red. Nitrogen adds purples and blues. During mild activity, these auroras stay near the geomagnetic poles where the field lines are already open to space. During a major storm, the entire pattern of currents and fields in the magnetosphere is reconfigured. The auroral oval swells and sag southward, dragging those lights over Canada, the northern United States, Europe, even the Caribbean in 1859. But the beauty hides something else going on at the same time: electricity. When you reshape a planet-sized magnetic field, you induce electric fields. Charged particles in the magnetosphere respond by flowing in enormous current systems that encircle the planet and connect down into the ionosphere. Those ionospheric currents, in turn, induce currents in the conducting ground below and in anything long and metallic on or near the surface. Telegraph wires in 1859, today high-voltage transmission lines, undersea cables, even long pipelines. Meanwhile, the same disturbed currents and energetic particles that light up the sky also mess with the upper atmosphere's ability to conduct and reflect radio waves. Frequencies that normally bounce around the globe can be absorbed or scattered. Others suddenly propagate farther than usual. To a 19th century telegraph operator, this showed up as phantom voltages and erratic signals. To modern aviators, satellite operators, and radio users, it shows up as dropouts, noise, and lost links. All of that auroras at strange latitudes, ground-induced currents, radio disruptions, flows from the same chain: a magnetized cloud hitting a magnetized planet, reconnection opening the gate, energy being stored in the tail, then explosively released. In 1859, that chain ran about as hard as we've ever seen it. The magnetosphere did its job. It took the hit for the atmosphere and for us. But it also turned that hit into something new, something our ancestors had never built for. A planet-wide electrical experiment, and the first people to really feel the consequences were sitting in front of wooden desks, their hands on telegraph keys, wondering why the sky was glowing and their wires were suddenly alive without any batteries at all. On the night of August 28, 1859, and again more violently on September 1st to 2nd, the magnetosphere tore open and the sky answered. If you'd lived in northern Canada or Scandinavia, you might have shrugged. Lights in the sky were nothing new there. Strange, yes, but familiar. A thing the world just did sometimes. But that's not what made 1859 different. What made it different was where people were seeing those lights. Newspaper editors in cities that had never, in living memory, seen an aurora suddenly had to find words for it. In Havana, Cuba, observers recorded a crimson glow spreading across the northern sky, so bright that people thought there must be a massive fire just over the horizon. In Jamaica, reports described a blood-red canopy that seemed to hang motionless overhead. In Monterey and San Francisco, California, the whole sky was described as like daybreak at midnight, with arches and curtains of pale light sweeping from north to south. In the American South, people were completely unprepared for what they were looking at. In Charleston, South Carolina, one witness wrote that the heavens glowed as if the whole prairie were on fire. In Savannah, Georgia, people rushed into the streets, convinced that some distant city was burning. In the Rocky Mountains, miners woke up in the middle of the night because their camp was suddenly as bright as dawn. Men started cooking breakfast, thinking they'd overslept, before realizing it was barely after midnight and the sunrise was in the wrong direction. In New York City and Boston, the show was even stranger. Accounts describe shimmering curtains, folding and unfolding across the sky. Rayed structures like ghostly searchlights fanning out from the horizon. Pillars of light that would brighten, fade, then suddenly erupt again, racing from one edge of the sky to the other in seconds. People compared it to an enormous celestial fireworks display, except this one didn't end. It just kept going, surging and pulsing and changing form. To people at those latitudes, this wasn't just pretty. It was uncanny. They had no cultural script for aurora over my house at 40 degrees north. So what actually was happening? Under quiet conditions, auroras cling to the geomagnetic poles. If you could draw them from space, they'd form two roughly circular ovals centered not on the geographic north and south poles, but on the magnetic ones. Most of the time those ovals stay put, wobbling a bit with solar activity, but rarely straying far. During a major storm, the whole system inflates and shifts. When that southward-pointed magnetic field in the CME locks onto Earth's field and starts pouring energy into the magnetosphere, the currents that drive the aurora strengthen and push equatorward. The bright ring of activity around each pole doesn't disappear. It swells and sags. The auroral oval stretches down over Canada, the northern United States, Europe, and in extreme cases like 1859, into the subtropics. Think of the polar lights not as a fixed crown, but as the rim of a bowl of water. Add a little energy, the water ripples. Add a lot, it sloshes over the sides. The Carrington storm was a planetary scale slosh. Magnetic field lines that normally only funnel particles into high latitudes were being twisted and reconfigured. The paths into the atmosphere opened farther from the poles, letting energetic electrons and ions dump into parts of the sky that almost never see them. Those colours people were struggling to describe weren't arbitrary. They were chemistry written in light. Most reports from low latitudes talk about red. Blood red, fiery red, a crimson arch. That's a clue. High altitude atomic oxygen, more than 200 kilometers above Earth, glows in a deep red line when it's hit by energetic electrons. At these heights, the air is so thin that excited atoms take a long time, fractions of a second, to drop back down and emit light. During a storm, with huge numbers of particles pouring in, those slow, high-altitude emissions can dominate, creating vast red veils and arcs that spread far from the poles, closer to the usual auroral zones. Witnesses talked about greens, whites, and even faint purples. Green is also oxygen, but lower down, around 100–150 kilometers, where de-excitation happens faster. The more dynamic, curtain-like motions, folds, rayed structures, sudden brightening and rippling often come from this lower region where the magnetic field lines are packed closer together and the incoming particles are more intense. purples and blues, rarer in 1859 accounts but still mentioned, hint at nitrogen molecules being excited and then radiating at shorter wavelengths. The motions people saw, the sky waving like a flag, fiery lances darting upward, bands marching from east to west, are snapshots of the magnetosphere settling and reconfiguring. You're watching, in real time, changes in electric currents hundreds of kilometers up. Bright patches mark where new bursts of particles are streaming down along field lines. Pulsations and flickering trace waves in the plasma above, like ripples on a pond where stones are being thrown in again and again. Down on the ground, though, nobody was thinking about oxygen emissions or plasma instabilities. They were trying to fit the sky into stories they already knew. Fires. Many observers, especially at low latitudes, interpreted the red glow as reflections from enormous conflagrations. Newspapers printed speculations that some distant forest, city, or even an entire region must be ablaze. In some towns, fire engines were reportedly dispatched toward an illusory horizon fire that didn't exist. War. The 1850s were a tense time. In the United States, civil conflict was looming. In Europe, revolutions were still within living memory. Some people took the red heavens as an omen of bloodshed, a literal war in the skies. Preachers used the event as a warning sign, a call to repentance. Letters and diaries talk about signs of the times and the heavens declaring judgment, wonder. Alongside the fear, there was awe. Farmers who'd never travelled far from home wrote about reading newspapers outside at midnight. Train conductors described their tracks lit clearly enough to see distant signals without lamps. In some places, people simply stayed up all night, staring upward, talking in hushed voices about what it all might mean. And then there were the attempts to explain. By 1859, scientists knew that auroras were linked to magnetic storms. The same days when compasses went haywire and telegraph systems misbehaved were often the days when the northern lights appeared. Some natural philosophers had already suggested a connection to the sun, even to sunspots. But nobody had a complete model. Maxwell's equations were just being worked out. Plasma physics didn't exist as a discipline. Space, as far as most people were concerned, was empty. So you get a patchwork of explanations. Some newspaper columns blamed electrical disturbances in the upper air. Others proposed that meteoric dust was burning in the atmosphere. A few more speculative writers invoked luminous ether currents. Early geomagneticians carefully logged compass deviations and compared them to auroral sightings, inching toward the idea of a global, connected phenomenon. They were groping toward the modern picture, but the tools weren't all there yet. And our picture of what they saw isn't perfect either. The historical record is noisy. We have beautifully detailed accounts from literate observers in cities and from scientific stations that happened to be active during those nights. We also have big blank patches, where newspapers weren't published, where people didn't write diaries, where clouds blocked the view. The sky could have been blazing and we'd never know. Even where records exist, they're filtered through human perception and language. One person's brightest day might be another's ghostly glow. The same red arc could be described as stationary by one observer and slowly moving by another, depending on how long they watched. Timekeeping wasn't always precise, locations weren't always reported accurately. Memory, especially when writing days later, is slippery. So when scientists today reconstruct how far the aurora reached in 1859, they're doing historical forensics. They sift through newspaper clippings, ship logs, observatory records. They triangulate latitudes, compare descriptions to known auroral forms, try to separate genuine low-latitude sightings from misidentified fires or atmospheric halos. There's still debate over just how close to the equator the lights got. Some claims put them over Hawaii, even near Central America. Others urge caution, pointing out ambiguous wording and second-hand reports. But even with all those caveats, one thing is clear. For a few nights in 1859, Earth's magnetic shield was so pumped full of solar energy that the usual rules about where the sky is allowed to glow simply broke down. People who had never seen an aurora, whose grandparents and great-grandparents had never seen an aurora, looked up and watched their atmosphere turn into a giant neon sign for something is happening out there. And while they were staring at the sky, something else was happening closer to the ground. The same storm that painted Havana and Honolulu with polar light was quietly driving currents through miles of copper wire, turning the 19th century internet into an uncontrolled experiment in planetary electricity. The telegraph operators were about to have a very strange night. While the sky was putting on its show, the real drama for the modern world was happening indoors, at little wooden desks with brass keys and coils of wire. To understand why, we have to talk about something that sounds abstract, but in 1859 was literally punching telegraph operators in the hands, geomagnetically induced currents. When the CMEs slammed into Earth and the magnetosphere started thrashing, the planet's magnetic field didn't just shift once and settle. It pulsed, it surged, it twisted and rebounded over minutes and hours. Every time the magnetic field through a region of Earth changed, it did something that Michael Faraday had worked out only a few decades earlier. Changing magnetic fields make electric fields. They have to. You can't get one without the other. If the magnetic field over a stretch of ground is rising and falling, nature responds by curling electric fields around those changes. And those electric fields push charges along any available conductors. Copper telegraph wires, for example. In 1859, the telegraph network was perfect for this. Long, nearly continuous lines of wire sprawled over continents, following railroads, crossing prairies, connecting cities. Many lines ran hundreds of kilometers without a break. From the point of view of that storm-driven electric field, these weren't just communication lines. They were antennas. A short wire won't pick up much. A loop of fence a few meters across might get a tiny nudge from the storm, not enough to notice, but stretch a conductor over 50, 100, 500 miles of varying magnetic field. And you give that induced electric field a runway. Even a feeble electric field acting over a huge distance can drive substantial voltages from one end of the line to the other. That's what geomagnetically induced currents, or GICs, really are. Slow, storm-driven currents pumped into the man-made nervous system draped over the planet. Telegraph operators didn't use that phrase. They just knew that their equipment was suddenly acting possessed. Accounts from Europe and North America talk about instruments overheating or melting. Relay coils ran hot. Spark gaps that were usually quiet crackled and spat. In some offices, the paper used to record dots and dashes reportedly began to scorch or smoulder when the current surged too high. Operators complained of shocks strong enough to make them drop the key. One Canadian operator later wrote that he saw streams of fire jump from his equipment during the peak of the disturbance. Part of this was simple overload. Telegraph systems of the day used relatively low-voltage batteries, wet cells supplying tens of volts to push a steady current along the line. They were designed for that known controlled power source. The storm didn't care about those design assumptions. It was adding its own uncontrolled voltage on top, sometimes reversing direction, sometimes spiking far above what the system was meant to handle. The result was confusion, messages garbled, relays clicked randomly. Needles on galvanometers swung violently for no apparent reason. In some places, companies shut down operation entirely, not because they understood what was happening, but because nobody wanted to sit at a desk where metal parts were spraying sparks, And then there were the stories that sound like science fiction. Operators unplugging their batteries and still sending messages. These reports show up in multiple accounts. On some long lines, especially in North America, operators supposedly agreed to disconnect their power supplies when the currents became dangerous, then discovered that enough auroral current remained in the wires to key messages for minutes at a time. One famous example describes a line between Boston and Portland exchanging intelligible traffic with no batteries attached at either end, just riding on whatever the storm was dumping into the conductors. If you know Faraday's law, this isn't magic. It's exactly what a changing magnetic field should do. Imagine the storm as a gigantic shifting magnet sweeping across the continent. Every time the field over that long wire changes, the effective loop formed by the wire and the conducting earth underneath it feels a push. The induced electric field drives a current. If that current flows in a roughly steady direction for a while, and if the telegraph circuit is closed through instruments and ground connections, it can mimic the role of the missing battery. What's less clear is how strong and how sustained those battery-free operations really were. Later retellings, especially in popular science books and magazines, tend to amplify the drama. You'll see claims that telegraphs ran for hours solely on auroral power, or that operators casually switched to solar electricity as if plugging into a new outlet. When historians go back to the original 19th century reports, the picture is more modest and more chaotic. We do have contemporaneous letters and log entries describing batteryless operation. We have reports of readable messages sent this way, but those same accounts usually mention the currents fluctuating wildly, messages being broken up by sudden surges, instruments still sparking dangerously. It wasn't a stable replacement power source, it was a noisy, erratic boost riding on top of a system that wasn't designed for it. There's also ambiguity in some of the narratives. An operator might say he disconnected the battery, but did every segment office along a long multi-station line do the same? Was there maybe still a power source feeding in from somewhere else on the circuit? In a world without standardized wiring diagrams and real-time system monitoring, it's hard to be certain. So the cautious reading is this. The storm absolutely induced currents strong enough to force operators to disconnect their batteries in some places, and in some cases those induced currents were sufficient, for short periods, to carry recognizable Morse code along the line. But telegraphs weren't serenely, reliably powered by the aurora all night. They were being hammered by a storm that kept shoving electricity into any long conductor it could find. That distinction matters, because it tells us something about both the physics and the vulnerability. The underlying mechanism, changing magnetic fields, inducing electric fields, those fields driving currents in long conductors, isn't just a curiosity from the telegraph age. It's the same basic process that modern power engineers worry about today. Only now, instead of single copper wires and modest relay coils, we've wrapped our world in continent-spanning high-voltage lines, transformers the size of houses, and a web of electronics that expects its electricity to be clean and predictable. In 1859, the worst that most operators faced was burnt paper, damaged instruments, and a few painful shocks. The same storm, translated into the technology of the 21st century, would not be nearly so quaint. So what actually broke in 1859? This is where the story usually drifts from history into disaster fan fiction. You'll see lines about global communications collapsing or the entire telegraph system going dark. That sounds dramatic. It's also not what the records show first. The real damage. We have solid documentation of telegraph instruments overheating, insulators cracking, and in a few cases, fires starting in telegraph offices. Papers from the time mention ignition of paper and other combustible material at key points in the network. Coils cooked, relay magnets were scorched. Some operators had to physically yank smoking equipment off the desk. There were temporary blackouts of service, especially during the most intense geomagnetic fluctuations. Some companies suspended operation for hours because the lines were either unusable or too dangerous to touch. On certain routes, messages simply stopped because signals were drowned in noise or the line voltage was all over the place. But step back, and the picture looks less like total collapse and more like a patchwork of malfunctions. While some lines were being fried, others were still operating, sometimes badly, sometimes almost normally. Newspapers the next day ran stories about the strange auroras and the telegraph disturbances that had been telegraphed to them. In other words, even at the height of the storm, enough of the network stayed alive for people to send reports about how broken things were. Why the unevenness? Part of it was geometry. Geomagnetically induced currents depend on how the magnetic field over a region is changing, how conductive the ground is, and how the wires are laid out. The storm didn't pour uniform electricity into every line. It created large-scale electric fields that pushed charges along some paths much more strongly than others. Long, roughly east-west lines at higher magnetic latitudes tended to get hammered. They spanned more of the magnetic disturbance and lined up well with the direction of the induced electric field. Lines over resistive geology, like the Canadian Shield, could build larger voltages end to end, because the earth underneath didn't easily short out the potential differences. Shorter lines, north-south runs, or routes over more conductive ground often saw less trouble. They weren't immune, but they were less tuned to the storm. Some inland offices reported only minor needle fluctuations and odd behaviour, nothing like the fireworks described along a few famous trunk lines. Then there's the technology itself. Telegraph systems in 1859 were both more vulnerable and more resilient than people imagine. They were vulnerable because they were almost tailor-made antennas, very long single-wire circuits with ground returns, lightly insulated sitting on wooden poles for hundreds of miles. From the storm's point of view, they were giant loops connecting different patches of Earth, perfect for driving slow DC-like currents. But once those currents got into the system, there wasn't much else for them to break. Circuits were simple: a battery, a key, a relay or sounder, maybe a recording register, and a ground plate. No microchips, no digital control systems, no sensitive power electronics watching every millisecond of the waveform. You could burn out a relay coil, sure, but you weren't going to cascade trip an interconnected grid or erase the firmware of half the country's infrastructure. In most cases, if something failed, an operator noticed it, swapped a part, and the damage stopped there. And those operators weren't passive victims, they improvised. When the instruments started sparking, some offices simply opened their keys and left them open, effectively breaking the circuit and letting the line float, while the worst of the disturbance passed. Others changed how they grounded the system, switching to alternative ground plates or disconnecting the ground entirely to cut the loop that the storm was using. Some companies rerouted traffic through less affected lines, using whatever regional links still behaved. There are reports of operators agreeing to use slower speeds, longer characters, or repeated messages to punch through the noise when the line was erratic but not unusable. And then there were the deliberate shutdowns. Not every outage was forced by physics. In several places, superintendents told their people to stop transmitting and step away from the equipment because it was literally shocking them. To a telegraph company defending a fragile set of instruments with no spares down the road, sacrificing a few hours of service made more sense than playing chicken with an invisible, unexplained power source. So, if we strip away the later embellishments, what we're left with is this: the Carrington storm caused serious, sometimes dangerous disruptions to telegraphy. It damaged equipment, started a few fires, and made parts of the network unusable for stretches of time. but it did not produce a long-lasting worldwide communications blackout. The impact was intense, uneven, and crucially, limited by the simplicity of the machines involved. That simplicity is the baseline we have to keep in mind. In 1859, the main long conductors on the landscape were telegraph wires, and the devices attached to them were rugged, electromechanical gadgets that either worked or didn't. The system had weak points, but it also had natural fire breaks. Individual offices, isolated batteries, local decisions. The world we've built since then is different in kind, not just degree. Our high-voltage transmission lines are longer and more interconnected than any telegraph network. Our transformers are huge, efficient, and exquisitely sensitive to slow DC currents that 19th century operators would barely have cared about. Our communications, control systems, and even market operations are fused into the same electrical backbone. In 1859, when the storm pushed current into the nervous system of the world, it hit something simple and clunky that could absorb a lot of abuse. If a comparable storm hits now, it won't be attacking Morse keys and wet cells. It'll be driving itself straight into the circulatory system of an electrical civilization through hardware and software that expect a world far quieter than the sun sometimes allows. So how do we actually know how big the Carrington storm was? We toss around phrases like the largest geomagnetic storm on record, as if someone in 1859 had a space weather app. They didn't. There were no satellites taking pretty images of the aurora, no spacecraft sampling the solar wind, no global sensor networks streaming data to a central server. What we do have is a scattered paper trail, and from that, scientists have tried to reverse engineer the violence of a storm that nobody back then quite understood. The backbone of that reconstruction is something called a magnetogram. By the mid-19th century, several observatories around the world had magnetic observatories, quiet rooms where delicate instruments tracked the Earth's magnetic field. These weren't digital sensors. They were often just small magnets or coils suspended on fibers, with beams of light reflected onto photographic paper or ink pens marking continuous wiggles as the field shifted. When the Carrington storm hit, those pens went wild. At Kew Observatory near London, the magnetometer traces shot abruptly off scale, slammed back, oscillated, and in some cases flatlined because the instrument couldn't keep up. Other stations in Europe, India, and North America recorded sharp, sudden deflections, the magnetic signature of a geomagnetic storm slamming into the magnetosphere and driving currents through the upper atmosphere. Those wobbly ink lines are our primary quantitative evidence. They show when the field began to change, how fast, in what direction, and how long the storm lasted. From them, modern researchers can estimate things like the strength of the global ring current, the magnitude of the disturbance near the ground, and how rapidly energy was being pumped into the system. But the magnetograms alone don't tell the whole story. They're like having a few seismometers trying to map a global earthquake. So scientists lean on proxies, indirect clues that, when combined, start to bracket how extreme the event must have been. One powerful proxy is the auroral boundary. Auroras don't just appear randomly. For a given level of geomagnetic activity, there's a rough latitude line below which the lights almost never show up. Push that line toward the equator, and you know the storm is flexing hard. In 1859, we have dozens of eyewitness accounts of aurora at astonishingly low latitudes. People in the Caribbean writing by auroral light, reports from Hawaii. In Colombia, close to the magnetic equator, observers described a blood-red sky and luminous arcs overhead. Take all those locations, convert their old geographic descriptions into modern coordinates, account for where the magnetic poles were in 1859, and you can draw a rough auroral oval for the storm's peak. The lower that oval dips, the more intense the storm had to be. Another proxy is the behavior of telegraph systems themselves. Remember those induced currents racing through long wires? The voltages needed to run telegraphs in 1859 were modest tens of volts, occasionally a few hundred. Yet operators reported disconnecting their batteries and still having strong, sometimes stronger currents driven purely by the storm. Keys sparked violently. Sounders chattered with no one touching them. Lines worked themselves for minutes at a time. By estimating the lengths and orientations of those lines, the typical resistance, the voltages usually employed, and the severity of the effects described, engineers can back-calculate rough electric fields at the Earth's surface. Those fields are tied directly to how rapidly the geomagnetic field is changing. Faster change, bigger induced fields, nastier telegraph fireworks. Timing matters too. We know when Carrington saw his white light flare. We know roughly when the first major magnetic disturbances hit, and when the most violent phase occurred. By aligning those times with modern knowledge of CME travel speeds, shock fronts and storm development, scientists can infer details about the solar eruption itself, how fast it must have been moving, how compressed the interplanetary magnetic field likely was, and how strongly it coupled to Earth's magnetosphere. Out of this mishmash of magnetograms, auroral sightings, telegraph reports and timing constraints, researchers try to assign numbers. They build indices. Today, space weather agencies talk about things like DST or KP, composite measures derived from many stations that describe how disturbed the global field is. You'll often see attempts to translate the 1859 observations into an equivalent DST value, as if we'd had a modern index running at the time. Those reconstructions tend to put Carrington at the extreme end of the known distribution. But the exact number? That's murky. Different groups, using different assumptions and weighting different data, can get significantly different answers. Some place it in the same league as the largest storms of the space age. Others argue it may have been substantially stronger than anything we've directly recorded. Part of the uncertainty comes from data gaps. Magnetometers in 1859 were few and far between, concentrated in Europe and parts of the British Empire. Large chunks of the globe simply weren't being measured. Even where instruments existed, their dynamic range was limited. When the trace shoots off the paper and disappears, you know the field changed by at least this much, but not how much farther it kept going. In some cases, critical minutes of data are missing because the instrument jammed or an observer adjusted it mid-storm, trying to keep it on scale. Calibration wasn't always perfect. Local timestamps can be off by minutes. All of these little errors ripple forward when you try to reconstruct global indices with modern precision. The proxies have their own limitations. Auroral reports are written by humans, not GPS receivers. Someone's overhead might mean 20 degrees from the zenith or just really high up. Cloud cover, moonlight and local light sources all shape what people saw and how they described it. Telegraph accounts of vivid but qualitative operators weren't logging exact currents and voltages while dodging sparks. So when you hear researchers debate whether Carrington was a DAST of minus 850 nanotesla or minus 1600, understand what that really means. They're not arguing over some absolute truth etched in a hard drive. They're arguing over which combination of incomplete, noisy 19th century clues best maps onto a modern yardstick that didn't exist at the time. This is why terms like Carrington class are fuzzier than they sound. In popular writing, it often gets used as a shorthand for really big geomagnetic storm. In the technical literature, it can mean several different things. Storms with auroral boundaries as low as 1859, storms with reconstructed DST beyond some threshold, storms with especially rapid onset and extreme rates of change. By some definitions, a 1921 storm qualifies. By others, The famous 1989 Quebec blackout event comes close. The 2012 near-miss CME that shot past Earth's orbit a few days after we'd been there is sometimes labelled Carrington class, based on its inferred solar wind properties, even though it never actually hit us. So when we ask, could we get another Carrington? We first have to admit that Carrington class isn't a single clean category. It's a cluster of extreme events, partly overlapping, defined through the fog of old data and the biases of modern metrics. In the next section, we'll step out of 1859 and look at that cluster. Other monster storms we've caught with modern instruments, near misses that barely missed Earth, and what they tell us about how often the sun really swings for the fences. When we finally get out of 1859 and look around, we realise something uncomfortable. Carrington wasn't a one-off miracle of celestial violence. It was one roll in a pair of loaded dice the sun has been throwing for as long as Earth has had a magnetic field. The first really useful comparison point shows up in May 1921. By then, we had more telegraph lines, early telephone systems, and better magnetic observatories. No satellites, no solar wind monitors, but enough infrastructure to notice when the sky decided to lean on the system. The 1921 storm hit hard. Magnetometers recorded a sharp, sudden disturbance comparable in some reconstructions to Carrington's main phase. Auroras pushed deep into lower latitudes again. People reported bright displays over New York, Madrid, even Samoa. In the United States, telegraph and telephone offices burst into literal flame as induced currents overheated equipment. Railway signal systems went haywire. In Sweden, control rooms reported persistent currents in telephone lines, strong enough to interfere with normal operation for hours. If you line up the proxies we just talked about, auroral boundaries, magnetic deflections, reports of induced currents, 1921 sits in the same extreme neighbourhood as Carrington. Some researchers think it might have rivaled or even exceeded it in certain ground-level effects, especially the speed and intensity of the magnetic changes. But there's a big difference between 1859 and 1921 that matters for us. In 1859, the world's longest conductors were telegraph wires. In 1921, high-voltage power systems were emerging, but they weren't yet as vast and interconnected as today's grids. The storm could start fires and wreck equipment, but it still wasn't pushing on a truly global, synchronized electrical machine. By 1989, that had changed. On March 13, 1989, a strong CME hit Earth and drove a geomagnetic storm that wasn't quite Carrington class by most indices, but it didn't have to be. It had the right structure at the right time, and it ran into a grid designed in a way that turned geomagnetically induced currents from a curiosity into a blackout. Over Quebec, the Earth's magnetic field began changing rapidly. According to Faraday's law, those changes induce electric fields in the ground. The geology of eastern Canada, high resistivity rock, poor at conducting electricity, forced those currents to look for an easier path. High voltage transmission lines fit the bill perfectly. From the grid's point of view, these geomagnetically induced currents, or GICs, looked like a slow DC component being pushed through a system built for AC, transformers, especially large extra high voltage ones, hate DC. It drives them towards saturation. The magnetic core can't handle the extra bias, so the device starts to behave non-linearly. Heat builds up. Protective relays trip. Voltage collapses. In Quebec, within about 90 seconds, that cascade turned into a province-wide blackout. 6 million people in the dark. No Carrington-level storm required, just a strong one, coupled efficiently into a vulnerable configuration. 1989 was a wake-up call because it showed loudly that You don't need the largest storm in history to break things. Grid vulnerability is as much about design, topology and regional geology as it is about the storm itself. Big transformers are critical, hard to replace, and not invulnerable. Some units in 1989 were damaged enough to need months of repair. Others elsewhere in the world under different storms have shown subtle but permanent degradation, insulation damage, gas bubbles in the oil, quiet failures that shorten their remaining life. Space weather had gone from interesting science problem to engineering and policy problem. Utilities started mapping GIIC flows, adding blocking devices, revisiting protection schemes. But the core lesson was blunt. Our infrastructure had grown big enough, long enough, and interconnected enough that it could now resonate with the sun. And then there are the shots we didn't take. In July 2012, a massive CME exploded off the sun. Its speed, internal magnetic field, and orientation, reconstructed from spacecraft data, put it firmly in the Carrington-class ballpark. The kind of event that, if it hit, would almost certainly have produced a storm as big as or bigger than anything we've seen in the space age. It missed us by about 9 days. The eruption blasted through the orbit of Earth, but Earth had already moved on. A NASA spacecraft, Stereo A, happened to be in roughly the right place, and it took the punch for us. Instruments there measured the solar wind properties and magnetic field that we can only infer for 1859. The implication is stark. We don't have to imagine hypothetical monster storms from scratch. We watched one go by, we just weren't standing in the intersection when it crossed. So what does all this say about how often the sun swings this hard? You'll sometimes see numbers thrown around. Carrington-class storms have a return period of 100 years, or 150, or 500. These estimates come from combining a relatively short space-age record, a few historical events like 1859 and 1921, and statistical models of solar activity and CME properties. They're useful, but they are not guarantees. A 100-year storm doesn't mean you get one neatly spaced every century. It's shorthand for an average probability, maybe a 1% chance per year over many centuries. You can get 2 in a few decades and then go quiet for 300 years. Or you can skate close twice in one solar cycle like 1989 and 2012 and still not have the truly catastrophic coupling. On top of that, our historical record is biased. We have good magnetic data for about 150 years, satellites for only a few decades, and before that we're reconstructing from ship's logs and scattered diaries. Extreme events are, by definition, rare. It doesn't take many missing entries to skew your sense of how often they happen. So the honest statement about recurrence is this. Large geomagnetic storms are normal for a magnetically active star like the Sun. Truly extreme Carrington-scale storms are probably uncommon, but uncommon on human timescales is not the same as never in my lifetime. Underneath all the differences between 1859, 1921, 1989, and 2012, there's a common thread. Every time, the basic physics is the same. Rapid changes in Earth's magnetic field induce electric fields. Those fields drive currents through any conductive path available: rocks, seawater, pipelines, railways, power lines, telegraph wires. The longer and more interconnected those conductors, the bigger the currents can become. And every time, the real damage doesn't come from a single component popping. It comes from interdependence. Telegraphs in 1859 weren't just wires. They were the nervous system of long-distance communication. Grids in 1989 and today aren't just copper and steel. They're tightly coupled networks tied into everything else we do: water, banking, transportation, data. Space weather exploits structure. The more tightly we've woven our systems, the more an invisible current, induced thousands of miles away can end up mattering in your living room. In the next sections, we'll zoom in on that structure. What modern power grids actually look like from a space weather perspective, how satellites and GPS fit into the picture, and why a storm that would have been a weird light show in 1859 could now thread its way through systems we barely notice until they stop. To understand why the next Carrington-level storm is a different kind of threat, you have to look at what we've built since 1859. Not the solar panels, not the phone chargers, the skeleton underneath all of it. Modern power systems aren't just wires that move electricity. They're enormous, synchronized machines stretching hundreds or thousands of miles, all trying to keep the same rhythm, 50 or 60 cycles per second, everywhere, all the time. From the sun's point of view, that's an opportunity. Remember those geomagnetically induced currents, GICs, we talked about with Quebec? They don't care about your local breaker box. They care about big loops of wire and easy paths into the ground. High voltage transmission lines are perfect. Picture two giant substations a few hundred miles apart, connected by a 500 kilovolt line. Each end is tied into the earth through grounded transformers, huge steel tanks filled with oil and copper windings, each one connected to buried grounding grids for safety and lightning protection. Now drop a strong geomagnetic storm on top of that. As Earth's magnetic field writhes and twists, it induces an electric field over large regions of the ground. That field pushes slow, DC-like currents through anything conductive. Bedrock, seawater, pipelines. But rock, especially in some regions, is a lousy conductor. Long transmission lines made of thick aluminum and steel are not. So the current takes the path of least resistance. It flows up one substation's ground grid, through the transformer windings, along the high voltage line, and back down into the earth at the other end. What you've accidentally built is a giant loop between two grounded anchors. A loop that the storm can drive current through, whether you like it or not. This is where transformers get into trouble. Under normal operation, they're elegant devices. AC current on the primary side creates a smoothly oscillating magnetic field in the iron core. That field induces a matching AC voltage on the secondary side. Everything rises and falls in a sine wave, neatly confined inside the magnetic capacity of the core. Add GICs, and you're sneaking in a DC bias. It's like leaning on one side of the sine wave. Instead of swinging equally positive and negative, the magnetic field gets offset. During part of the cycle, the core gets pushed deeper into magnetization than it was designed for. At a certain point, it can't magnetize any further. It saturates. Once that happens, the transformer stops behaving like a transformer for part of each AC cycle and starts behaving like a big chunk of metal being hammered with current. Currents spike. The waveform distorts, throwing ugly harmonics back into the grid. The magnetic field leaks out of the core and into parts of the structure that were never meant to see that kind of flux. Windings heat up. The oil that's supposed to cool and insulate them heats up too, sometimes forming gas bubbles. Insulation ages in hours the way it normally would over years. If this continues long enough, you can literally cook the transformer from the inside. Grid protection systems are designed to prevent that, but they weren't originally written with space weather in mind. Relays see the odd currents and distorted voltages and make the only decision they can. Something's wrong, trip the line, isolate the problem. Do that to one line, and you can usually reroute power. Do it to several key lines and transformers at the same time, across a large area, while the storm is still pushing on the system, and you start to get the thing grid operators really fear, cascading failure. Here's how that can unfold. You lose a major transmission corridor because GICs are saturating transformers and tripping protection, power that was flowing along that path has to go somewhere else, so it reroutes through other lines and transformers that were already heavily loaded. Their currents increase, their voltages sag, their protection margins shrink. Meanwhile, the harmonics and voltage swings from partially saturated transformers confuse some relays and stress others. A few more lines trip, a big generator sees the grid voltage wobble outside its comfort zone and disconnects to protect itself. With less generation supporting the same load, voltages dip even further. Keep pushing, and you can hit a tipping point, a voltage collapse. It's not that everything explodes, it's that the network can no longer maintain stable voltages and synchronism. Loads drop offline, generators trip out, sections of the grid separate from each other. In the worst case, you end up with a patchwork of dark regions and a few surviving islands of power, each one trying to keep its own little mini-grid alive. The scary part is that you don't need every transformer to fry for this to happen. You only need enough key components to misbehave at the wrong places at the wrong time. So how bad could this get under a true Carrington-class event? This is where the discussion gets careful. Most experts agree on some broad points. Geomagnetic storms absolutely can drive GICs in long transmission lines. Large, grounded transformers do experience saturation and heating under those conditions. Cascading outages are a real risk. 1989 showed that conclusively on a regional scale. It's also widely accepted that extra high voltage transformers, those big 400, 500, 765 kilovolt units, are critical, expensive and slow to replace. Many are custom built. Lead times can be months to years. You can't just pull one from a shelf like a toaster. But beyond that, the scenarios start to fan out. How many transformers might see damaging levels of GIC in a worst-case storm? How many would just get hot and annoyed versus actually failing? How far and how long would blackouts spread? Those answers depend on messy details, the exact structure of the storm's magnetic field, how fast it changes, local geology, grid topology at that moment, the protections and operating procedures in place, even what season it is, and how heavily the system is loaded. Some studies paint very dire pictures. Multiple regions with long-lasting blackouts, dozens or hundreds of large transformers damaged, years of constrained power supply. Others, using different assumptions and models, suggest more moderate outcomes, serious but mostly temporary outages, some damaged equipment, but far from civilizational collapse. The honest thing to say is, we know enough to be worried, not enough to be precise. Even in the moderate cases, though, restoration is not a flip-the-switch event. Imagine a storm knocks out power across a big area, but only a handful of major transformers are actually damaged beyond immediate use. You still have to stabilize the surviving grid islands so they don't trip themselves offline. Carefully bring generators back in sync. Re-energize transmission lines without overloading the remaining transformers. Restore power to critical loads, hospitals, water systems, data centers, before everyone else. All while monitoring for hidden damage that might show up only when you stress the system again. If some transformers are permanently lost, you might have to run with weird power flows for months, relying on long detours through neighbouring regions. That can mean rolling blackouts, voltage limits, or strict industrial curtailments even after the lights are back on for most people. And that's assuming the broader supply chain is intact. In a truly large event, you could have simultaneous problems with satellites, communications, fuel logistics, the very tools you'd normally use to coordinate a complex restoration. The key difference between 1859 and now is not that space weather suddenly became more dangerous. It's that we've wired ourselves into a machine large enough that when the sun leans on it, the consequences aren't local anymore. But the grid is only one layer of that machine. Above it, literally, is the other modern structure the Sun can grab. The fleets of satellites quietly handling navigation, communication and timing. In the next section, we'll move off the ground and into that orbital shell, where a Carrington-class storm doesn't have to melt hardware to cause cascading trouble. If the power grid is the nervous system of our civilization, satellites are the senses and inner ear. They're how the planet knows where it is, what the weather is doing, what time it is, and who's talking to whom. And just like your senses, you mostly notice them only when they fail. A Carrington-level storm doesn't have to blast satellites to pieces to be a problem. It just has to shove Earth's upper atmosphere and radiation environment out of their normal range, long enough in enough different ways that the whole orbital shell starts behaving strangely. Start with something that sounds almost harmless, atmospheric drag. We tend to imagine space as empty the moment you're above the blue sky. It isn't, even at 300 or 400 kilometers up, where the International Space Station and lots of Earth observation satellites live. There are still atoms of air. Not many, but enough that as a satellite plows through them at 7 or 8 kilometers per second, each tiny collision steals a bit of energy, slows it down, and lets gravity pull it slightly lower. Under quiet solar conditions, mission planners know roughly how fast that happens. They budget fuel for reboost maneuvers. They know when an old satellite will re-enter and burn up. Now turn on a major geomagnetic storm. Energetic particles pour into the upper atmosphere, heating and puffing it up like a thin shell of gas swelling outward. The density at a given altitude can jump by factors of 2, 5, 10 for a while. Suddenly, every satellite in low Earth orbit is flying through thicker air than anyone expected. Drag spikes, orbits shrink faster, ground tracks shift. In February 2022, a relatively modest geomagnetic storm caused SpaceX to lose most of a batch of newly launched Starlink satellites. They were in low initial orbits, still climbing when the atmosphere thickened under them. Drag increased. They couldn't gain enough altitude, and they re-entered within days. That was a warning shot under pretty tame conditions. Scale that up to a storm in the Carrington class, and you're not just losing some new hardware. You're watching a whole shell of satellites have their orbits perturbed at once. Some drop lower than planned, some climb slightly as operators fire thrusters to compensate. The carefully mapped ballet of who passes over what ground station at what time becomes harder to predict. Collision risk models, which depend on knowing orbits precisely, start to wobble. Tracking networks can adapt, but only if their own sensors and communications are working cleanly. And those are under attack too by radiation. When the sun throws a tantrum, it doesn't just thicken the atmosphere. It floods near Earth space with high-energy particles and twists magnetic fields that can trap and accelerate them. Satellites move through this storm of charged bullets, with electronics designed for a calmer sky. Inside those electronics, everything depends on individual bits of information staying exactly what they are. 0 or 1, off or on. An energetic particle doesn't care. It plows through a microchip, leaves a tiny trail of ionization, and can flip a bit from one state to the other. That's called a single event upset. Most of the time, it's harmless. A cosmic ray flips a bit in a pixel of a camera sensor, and you get a bright speck in an image. Or it toggles a memory cell that some error correction code quietly fixes. You never notice. But in extreme radiation conditions, the rate of those hits goes up. A lot. Now, you're not dealing with an occasional glitch. You're dealing with a constant background of tiny random pokes to the brain of a spacecraft. Sometimes that just confuses software, causes reboots, or trips safe modes. Sometimes in the wrong place at the wrong time. It can corrupt navigation data, scramble a configuration file, or make a control system misbehave. Over years, radiation does something slower and uglier. It degrades sensors and hardware. Detectors for imaging and weather sensing begin to accumulate hot pixels and noise. Solar panels slowly lose efficiency as their crystal structures are damaged. Insulators darken, analog circuits drift out of spec. A Carrington-class event, with its huge dose of energetic particles, would be like aging certain parts of satellite fleets in fast forward. Some satellites are hardened for this. Military and some navigation spacecraft use radiation-tolerant components, thick shielding, conservative designs. But there's a trade-off. Hardened electronics are heavier, more expensive, and often lower performance. So a huge number of commercial communications, imaging, and small satellites are built with lighter, cheaper parts and minimal shielding. They're designed around good enough protection for the storms we've actually seen in the space age so far. Push beyond that and the margin shrinks. Now connect this to what those satellites actually do. Communication satellites, especially in geosynchronous orbit, are the quiet backbone for TV. Some internet backbones, military links, and a lot of emergency communications. They beam signals across oceans and into remote areas where fibre doesn't reach. During a severe storm, their radio links can get noisy or drop out altogether. High-frequency noise in the ionosphere scatters signals. Increased radiation causes onboard receivers and amplifiers to misbehave. To protect themselves, operators might turn off sensitive instruments, rotate spacecraft into safer orientations, or partially power down payloads. Each one of those choices shows up on the ground as degraded bandwidth, lost channels, slower connections, or complete outages for certain regions. Timing services ride on these systems too. Navigation constellations like GPS, GLONASS, Galileo, Beidou aren't just for cars and smartphones. Their precise atomic clocks feed timing to financial networks, cellular base stations, power grids, and data centers. Even systems that don't use GPS often rely indirectly on timing derived from it somewhere upstream. Radiation and ionospheric chaos hit those constellations from two directions. In space, the satellites themselves can suffer clock glitches, receiver errors, or safe mode entries. On the way down, their signals pass through a disturbed ionosphere that delays and bends radio waves in ways the usual correction models don't fully capture. Navigation receivers on the ground depend on predicting that delay. Get it wrong, and your position solution starts to wander. For a phone trying to draw a blue dot on a map, that's an annoyance. For an aircraft on an automated approach, a ship in a narrow channel, or a high-frequency trading system timing orders to microseconds, it can be a serious problem. So what do we do about it? Engineers aren't walking into this blind. There are playbooks. Most large operators have space weather procedures. When solar monitors see a big flare and coronal mass ejection headed our way, they can switch satellites into safe mode, simplifying operations and shutting down non-essential systems. Rotate spacecraft to minimize the cross-section exposed to the worst particle flux. Lower data rates and add extra error correction to communications links. Delay critical maneuvers, software uploads or deployments until the storm passes. Hardware helps too. Shielding, layers of aluminum or other materials, soaks up part of the particle flux before it reaches sensitive components. Redundant systems allow a satellite to shrug off some damage. Radiation-hardened chips resist upsets better than commercial parts. But every mitigation has limits. Safe mode keeps hardware alive, but while a satellite is in safe mode, it's not doing its job. You can't take every weather satellite, every navigation satellite, every communications relay offline for days without the ground feeling it. Shielding can't be infinite. Every extra millimetre means more mass, more launch cost, less payload. Radiation-hardened parts lag behind cutting-edge chips. So satellite designers balance robustness against performance and price. Operationally, you can only respond to storms you see coming. A fast, complex event can still surprise you, hitting before all precautions are in place, or evolving in ways the models didn't anticipate. And many of the newest players in orbit, constellations of thousands of small satellites, operate closer to the edge. Lower altitudes, smaller radiation margins, tighter budgets. Which brings this back down to Earth. Every time you check a weather forecast based on data from polar orbiting satellites, call someone through a link that quietly bounces through a GeoBird, or use a debit card in a system timestamped by GPS, you're leaning on that invisible infrastructure. A Carrington-class solar storm doesn't have to be a single catastrophic blow to knock it around. It can be a global annoyance storm, orbits shifting, signals degrading, services flickering in and out. Not enough to send us back to the 1800s, but enough to make the modern world stumble. And space is only part of the story. The same timing signals and radio links that keep satellites coordinated also stitch together aircraft routes, long-distance radio and global internet backbones. In the next section, we'll follow those threads down through the atmosphere, into the systems that guide planes, ships and bits across the planet, and see what happens when the sky itself stops behaving the way our technology expects. When most people think of GPS, they picture a phone figuring out where it is. Blue dot, moving car, turn-by-turn directions. But to a solar storm, GPS isn't. The map app, it's a fragile radio conversation between space and a churning, electrically active upper atmosphere. And in a Carrington-class event, that atmosphere stops behaving politely. Those navigation signals have to pass through the ionosphere, a layer of thin, partially ionized gas about 60 to 1,000 kilometers up. Under quiet conditions, we know roughly how dense it is, how it bends and delays radio waves, how its electron content changes through the day. GPS receivers use models of that behavior to correct for the extra travel time. Now throw a major geomagnetic storm into the mix. Energetic particles slam into the upper atmosphere, dumping energy, tearing electrons loose, stirring everything into turbulence. Instead of a smooth, predictable layer, you get patches and bubbles of higher and lower density, shifting minute by minute. Engineers call it scintillation. The signal flickers, refracts, and sometimes vanishes altogether along certain paths. To a GPS receiver that looks like the satellites are jittering in the sky. The calculated distance to each one starts to wander. The algorithms try to make sense of it, to fit a stable position to unstable inputs. Sometimes they can. Accuracy degrades from centimeters to meters, from meters to tens of meters. Sometimes they can't. The solution jumps around, or the receiver gives up and drops lock. For everyday uses, that's annoying. Your car thinks you're on the frontage road instead of the highway. Your hiking app draws a squiggly line instead of a clean track. For systems that depend on centimetre-grade accuracy, precision agriculture, surveying, construction, some forms of automated landing, it's a showstopper. They either have to fall back to less precise modes, or pause operations entirely until the sky calms down. But position is only half of what these constellations provide. The other half is time inside each GPS satellite, and its cousins in other systems sit atomic clocks. Hyperstable, carefully calibrated, maintained to within billionths of a second. The whole system works because those clocks march in lockstep. The receiver on the ground isn't just measuring distance, it's solving for its own time offset as well. That precise time leaks everywhere. Cell towers use GPS-disciplined clocks to stay synchronized, so your phone can hop between them smoothly and so data packets arrive in the right order. Financial exchanges use it to timestamp trades to microseconds, to enforce rules about who really placed an order first. Power grids use it to keep generators in phase and to know exactly when a fault happened on a line hundreds of kilometers away. Data centers use it to coordinate logs and transactions across continents. GPS disciplined means the local clock, often an oven-controlled crystal oscillator or local atomic reference, constantly nudges itself to match what the satellites say. It's like a whole civilization of clocks listening to a quiet metronome in the sky. Disturb that metronome and the drift begins. In a strong storm, satellite signals can be delayed more than usual, or fade in and out, or carry subtle errors. Onboard clocks, stressed by radiation, might experience more glitches or require resets. As the timing stream becomes noisy, receivers have to decide, do they trust the last good value and coast, or keep following a signal they know is being warped? High-end systems can hold over for a while, relying on their own internal stability. But the longer they're cut off from clean updates, the more error creeps in. Nanoseconds become microseconds, then milliseconds. For some applications, that's still fine. For others, it's the difference between coherent and chaos. Now layer this onto the physical plumbing of the internet. The actual data of the global network mostly travels through fiber optic cables, glass threads under streets and oceans, not through satellites. Those fibers don't care what the ionosphere is doing. A coronal mass ejection doesn't melt glass in a conduit 2,000 meters below the Atlantic. But those cables aren't magically self-aware. They're stitched together by repeaters, amplifiers, and landing stations that all depend on clean power and synchronized equipment. Undersea cables have their own vulnerabilities. The fibers carry light, but running along the same route is a copper conductor used to send power to amplifiers spaced along the seabed. That power usually comes from stations on land. Those stations sit on coastal grids, with transformers and protection systems that respond to geomagnetically induced currents, just like inland infrastructure. If a severe storm knocks out or destabilizes shoreside power, you can't keep pumping energy into thousands of kilometers of seafloor hardware indefinitely. Some cables have backup generation, some routes can be rerouted, but redundancy only goes so far when multiple landing points on multiple continents are all being stressed at once. On land, major backbone routes long-haul fiber between cities often follow power corridors or rail lines. Their repeaters live in huts and data centers tied into the grid. Lose power there, and unless generators kick in and fuel keeps flowing, the light in those fibers goes dark even though the glass itself is fine. So what actually breaks in a realistic extreme storm? It's unlikely that the internet simply vanishes worldwide. More plausible is a patchwork of degradation. GPS-based services see accuracy swing wildly in some regions, especially at high latitudes and near the day-night boundary, where ionospheric disturbances are strongest. Aviation and maritime navigation may have to revert to older systems, ground-based beacons, inertial navigation, radar, while GPS is flagged as unreliable. Telecom networks, especially cellular systems that lean heavily on GPS timing, start dropping calls, mishanding handoffs, or losing synchronization between base stations. Operators may fall back on internal timing references, limiting capacity or range to keep things stable. Some 4G and 5G features that depend on tight timing simply stop working cleanly. Financial centers could see exchanges preemptively widen trading windows, relax ultra-fine timestamp rules, or even pause certain high-frequency strategies if timing confidence drops below agreed thresholds. That's not because anyone lost track of seconds. It's because nobody wants to argue in court over whose microsecond is true when the space-based clock has been wobbling. Undersea and terrestrial backbones might experience regional outages where power problems, not the cables themselves, take equipment offline. Traffic gets rerouted through remaining paths, increasing latency and congestion. Some regions become effectively more distant from each other on the network map, not because the Earth got bigger, but because the easy shortcuts blinked out. The dangerous part isn't any one of these failures. It's their interdependence. Power grids use communications networks and GPS timing to manage loads and detect faults. Communications networks use the grid to stay energized and use GPS to stay synchronized. Financial systems rely on both. Emergency response relies on all of the above. A big geomagnetic storm hits the grid first. Lines saturate, transformers heat, operators shed load or lose regions. As blackouts spread, some cell towers switch to batteries and generators. Data centers spin up diesel. For hours or maybe days, things limp along. Then fuel runs low in places. Maintenance crews can't reach certain sites quickly because traffic lights are out and rail signals are confused. Some backup systems fail to start because a GPS-disciplined clock threw them a surprise. The more pieces stumble, the harder it is for the others to stay upright. From the sidewalk, this doesn't look like the end of the world. It looks like dropped calls, slow websites, ATMs temporarily unavailable, credit card machines stuck in offline mode, flights delayed because navigation systems are flagged as degraded news stories about technical issues following the solar storm. But underneath, the nervous system and the clocks that keep it all in rhythm are under stress from the same invisible punch that once lit up 19th century telegraph wires. In the next section, we'll drop even closer to the human layer. Airplanes in flight, radio operators on the ground, cosmic rays nudging doses higher at cruising altitude, and how in a sky crackling with solar anger, we keep people safe while the instruments flicker. At ground level, a solar storm is mostly an electrical and timing problem. In the sky, it becomes a radiation and radio problem too. Start with those long-distance radio links that don't need satellites at all, HF, or high-frequency radio. For most of the 20th century, this was how ships talked to shore, how transoceanic flights checked in, how militaries and remote outposts stayed connected. HF works because the ionosphere, that same layer that bends GPS, can also act like a mirror. You bounce a signal up, it reflects, and comes back down thousands of kilometers away. No cable, no satellite, just sky physics. A geomagnetic storm scrambles that mirror. When intense X-rays and extreme ultraviolet light from a big flare hit the dayside atmosphere, they supercharge the lower ionosphere, especially a region called the D layer. Instead of being transparent to HF, it turns into a sponge. Signals that used to bounce now get absorbed. To the operator, the band just dies. This is what scientists call an HF radio blackout. It doesn't hit everywhere equally. The polar regions get the worst of it. Remember those energetic particles funneled down by Earth's magnetic field? Near the poles, that funnel opens into the atmosphere. Storm-time particle showers dump energy straight into the ionosphere overhead, making it even more disturbed, even more absorptive. HF links that route over the Arctic, perfect for Great Circle airline routes between North America and Asia, or Europe and Asia, can go from reliable to useless in minutes. That's why airlines care so much about space weather. Modern jets don't fly blind if HF goes away. They have satellite communications, VHF radio near land, inertial navigation that doesn't need GPS from minute to minute. But there's a catch. Polar routes often lie outside normal ground radar and VHF range, and in an extreme storm, satellites themselves may be degraded or forced into safe mode. So when space weather bulletins warn of severe polar cap absorption, dispatchers start making choices. One option is rerouting. Instead of the shortest path over the pole, flights arc further south, staying within better radio coverage and away from the worst particle precipitation. That adds fuel burn, time and cost, but it keeps communications more robust. Another lever is altitude. Radiation from cosmic rays and solar particles drops as you descend into thicker atmosphere. At typical cruising altitudes, 30 to 40,000 feet, crews and frequent flyers already get more radiation than people on the ground. During a major solar event, that dose can spike, especially at high latitudes where magnetic shielding is weakest. We're not talking comic book levels. Regulations and monitoring programs exist for exactly this reason. Airlines track cumulative crew exposure. Space weather centers publish dose rate estimates in near real time. If a storm is big enough, operators can choose to fly a bit lower on certain routes, shaving off some extra dose at the cost of higher fuel use. In truly extreme scenarios, they can cancel or delay polar flights entirely until conditions ease. This isn't hypothetical policy written in a binder nobody opens. It already happens on a smaller scale. Strong but not apocalyptic storms in the last few decades have triggered real-world reroutes, HF outages and temporary restrictions on the most northerly tracks. And HF isn't just for airlines. Emergency services, maritime operators and militaries still use HF precisely because it doesn't depend on satellites or dense infrastructure. When earthquakes or hurricanes knock out local networks, HF can reach beyond the disaster zone. When a conflict threatens satellites, HF is one of the backups. But you can only rely on it if you know when it's going to vanish. That's why space weather is baked into their planning. They train for degraded HF conditions, for no HF windows along certain paths, for switching to alternate frequencies, different propagation modes or backup satellite channels when the ionosphere turns hostile. They rehearse lost-com procedures for aircraft and ships, predetermined routes, timing and altitudes that let traffic keep moving safely, even if voices go silent for a while. Underneath all of this is a mix of hard physics and open-ended uncertainty. We understand in a textbook sense why X-rays spike the D layer, how charged particles follow magnetic field lines, how air density shields radiation. We can calculate that dropping from 39,000 feet to 31,000 feet cuts dose by a predictable fraction. We can model which HF bands are likely to be blacked out given a certain level of solar flux. What we can't pin down perfectly is the exact choreography of an extreme storm, how long the worst conditions will last along a specific flight path, how deep particle penetration will be over one polar corridor versus another, how multiple flares and CMEs might stack their effects over days. So aviation and radio planners don't bet everything on precision. They work with ranges and thresholds. If an event crosses a certain line, polar HF is treated as unreliable. If dose projections pass another, altitudes or routes change, the science sets the guardrails. Human judgment fills in the gaps. As we move higher toward astronauts in orbit and hardware beyond the magnetosphere, those guardrails change again. The same storm that makes your HF radio go quiet might be a life-threatening radiation event for a crew on the wrong side of Earth. And that's where we're heading next. What solar storms do to machines and people when there's nothing but vacuum between them and the sun. If you're an airline dispatcher, a grid controller, or the person responsible for $1 billion satellite, you don't just care that storms happen. You care about warning time. So how much do we actually get? Everything starts at the sun. The most basic thing we still watch, just like Carrington did, is sunspots. dark, magnetically tangled regions marching across the solar disk. They're not dangerous by themselves. They're more like pressure gauges. Big, complex sunspot groups are where the most powerful flares and CMEs tend to explode. Today, nobody's sketching them by hand. We have full-disk solar telescopes in multiple wavelengths, mapping magnetic fields across the surface. Forecasters at places like NOAA's Space Weather Prediction Center and NASA can see when a region's magnetic field is twisted into a shape that screams unstable. They can estimate its flare potential: minor, moderate, major. It's like watching thunderstorms build along a cold front. Probabilistic, not certain, but better than nothing. Then we watch for the actual explosion. When a flare goes off, that part of the sun brightens in X-rays and extreme ultraviolet within seconds. Spacecraft like the GOES weather satellites carry instruments that constantly measure the sun's X-ray output. A spike tells forecasters, a flare just happened, and here's roughly how big it is. That's our shortest warning window. The photons from that flare race to Earth at light speed. 8 minutes, give or take. By the time we know the flare occurred, the X-rays and UV that cause radio blackouts are already arriving. For HF communications, this isn't a forecast, it's essentially nowcasting. You get a few minutes of heads up at best. Then the delayer lights up and the bands die. The slower punch is the CME if there is one. Not every flare launches a big CME, and not every CME is aimed at us. To see those, we use coronagraphs, telescopes that put an artificial eclipse disk over the bright solar surface, so the faint outer atmosphere, the corona, becomes visible. In coronagraph images, a CME looks like a cloud or halo of plasma lifting away from the sun. From those images, forecasters can estimate speed and direction. A fast, wide CME heading roughly along the Sun-Earth line is the kind that makes people sit up straighter. This is where the lead time looks impressive on paper. A typical CME takes 1 to 3 days to reach Earth. The fastest ever recorded, including the 1859 Class 1s, can do the trip in under 18 hours. That sounds like a luxury compared to 8 minutes. But 1 to 3 days hides the messy part, uncertainty. The first problem is geometry. From a coronagraph sitting near Earth, you're looking at a 3-dimensional structure flattened onto a 2-dimensional image. It's like trying to judge the exact speed and path of a car based only on its shadow. You can estimate, but error bars are big. The second problem is structure. A CME isn't a uniform blob. It's a twisted magnetic bubble, maybe with multiple substructures moving through a solar wind that's already full of its own turbulence. Along the way it can slow down, speed up, merge with other CMEs, or be deflected by high-speed streams. Models try to account for this, but it's like predicting the exact shape of a hurricane 3 days out, not just landfall. And then there's the key detail that matters most for Earth: magnetic orientation. Earth's magnetic field near the day side points mostly north. If the CME's embedded magnetic field arrives pointing north too, the two fields tend to slide past each other with relatively modest coupling. If it arrives strongly southward, the fields interlock and energy pours into the magnetosphere far more efficiently. Same speed, same density, radically different impact. The catch is that from a coronagraph, we can't read that orientation directly. We usually don't know whether the incoming cloud is magnetically loaded for a big storm until it's almost on top of us. That's where a different class of spacecraft comes in. Solar wind monitors parked about 1.5 million kilometers upstream near a gravitational balance point called L1. Missions like ACE, DSCO-VR, and now the European Space Agency's Solar Orbiter in some configurations sit in the solar wind, sampling the flow in real time. When a CME reaches them, their instruments record density, speed, temperature, and, critically, the magnetic field direction. From L1 to Earth is about 30 to 60 minutes of travel time for typical storm speeds. In a true super-fast event, maybe only 15-20 minutes. That's our real, actionable warning for the worst geomagnetic part of the storm. During that window, alert systems go from something's coming to this is going to be bad right now. Space weather centers issue alerts on a graded scale: minor, moderate, strong, severe, extreme. Grid operators receive these bulletins and can start implementing storm procedures, reconfiguring which lines are in service, reducing transfers on long, vulnerable corridors, bringing extra reactive power support online, delaying maintenance that would leave the system less flexible. Satellite operators do something similar. With enough lead time from coronagraph-based forecasts, they can plan to switch into safe modes during the expected impact window, reducing non-essential operations, pausing delicate maneuvers, scheduling software uploads, or orbital adjustments away from the peak disturbance. As the CME passes L1 and that final magnetic orientation becomes clear, they refine those plans. If the field is strongly southward and densities are high, radiation belts are likely to swell and drag at low Earth orbit altitudes may spike. That can mean delaying some burns, tightening tracking, and bracing for more single event upsets in onboard electronics. Aviation and HF users rely on a slightly different set of alerts: warnings of radio blackouts, radiation storms, and polar cap absorption. Flare detections and solar particle event forecasts tell them when certain routes or altitudes are likely to be compromised. They can't move airplanes in 8 minutes, but they can decide what tomorrow's flight plan should look like, or whether to keep a plane south of a certain latitude as conditions evolve. All of this creates a layered defense: long-range, fuzzy warnings from sunspot monitoring and coronagraphs, medium-range planning based on CME models, and short-range, high-confidence alerts from solar wind monitors at L1. The catch is that none of it stops the storm, it only buys time. And that raises the next question, the one that really decides how bad a modern Carrington event would be, given hours, or even just tens of minutes of warning. What can we actually do in the physical world to blunt the impact? How much of our grid, our satellites, and our communications can be hardened or deliberately powered down in time, and what has to ride out the blast no matter what? The obvious fantasy solution is simple: just make everything Carrington-proof. The reality is way more awkward. We can't bubble wrap a civilization. We can only make it a bit harder to break. Start with the grid, because that's where geomagnetic storms become blackouts, which cascade into basically everything else. The main villain there isn't lightning-style surges. It's slow, DC-like currents, geomagnetically induced currents, or GIC, sneaking in along long transmission lines and through the ground. Those currents push transformers into weird operating zones, overheat them, and distort voltages. One class of fix is basically, don't let those currents in. You can install GIC blocking devices on vulnerable lines. These are specialized pieces of hardware, often based on capacitors or clever switching schemes, that interrupt the low-frequency DC component while still letting normal AC power flow. Think of them as check valves for geomagnetic sludge. Utilities in some high-risk regions, like parts of Canada and Scandinavia, have already started deploying them on key corridors. They're not magic shields. They add complexity, cost money, and can fail. But they shift the odds. A storm that might have pushed a line into dangerous GIC levels instead becomes uncomfortable but survivable. Then there's operational defense. If you know a strong storm is coming, grid operators can reduce power flows on the longest, most exposed lines. Lower loading means more headroom if transformers start heating up. They can bring extra generation online closer to demand centers, so you're not leaning as hard on cross-continent transfers. They can temporarily avoid certain grid configurations that are known to be GIC magnets. This is unglamorous stuff. It's the electrical equivalent of sandbagging and moving furniture upstairs before a flood. You're accepting some inefficiency, maybe a bit more congestion or higher prices for a day, in exchange for lowering catastrophic risk. Improved grounding is another quiet hero. When geomagnetic fields fluctuate, electric fields build up in the Earth. How that translates into actual currents depends on where the low-resistance paths are. Better, more uniform grounding of substations and towers can help control where those currents go. Instead of funneling huge DC flows through a few vulnerable transformers, you give them more benign paths into the ground. None of this makes the risk vanish. It turns grid-wide, months-long collapse into regional days to weeks disruption in many scenarios. That's still bad. It's also a lot better, but some bottlenecks are stubborn, and transformers are at the top of that list. Extra high-voltage transformers, the giant ones at major substations, are not commodity items. They're custom-engineered for specific voltages and grid configurations. They can weigh hundreds of tons. Manufacturing one can take a year or more, even in normal times, with steel, copper, and specialized labor all lined up. Transport is its own puzzle. You don't just throw one of these on a truck and drive down the interstate. Bridges, rail curves, road grades, all of it matters. Sometimes replacing a transformer means weeks of logistical choreography just to move the thing. So one obvious mitigation is have spares. There are programs like the US, grid assurance and STEP initiatives, where utilities pool resources or commit to maintaining regional spare fleets. Some countries have national strategic stocks of large transformers, but you can't realistically stockpile one-to-one replacements for every critical transformer on Earth. The units are expensive, millions to tens of millions each, and you have to maintain them, store them, test them. And a truly global superstorm wouldn't damage every transformer equally. It would fry some, stress many, and spare others for reasons tied to local geology and configuration. So planning becomes a triage problem. Which substations absolutely must be restorable first? How interoperable can we make replacement units? How do you prioritize rail capacity and heavy haul routes after a storm when multiple regions are shouting, "We need it now, move upstream into orbit"? And the problem looks different, but the logic is the same. Satellites can't run to the hardware store. Whatever protection they have to launch with. Designers already bake in a lot. Sensitive electronics can be shielded with aluminum or specialized materials to absorb some radiation. Critical components can be triplicated, with voting logic so that if one chip starts spitting nonsense after a particle hit, the other two outvote it. Memory can be scrubbed, constantly checked and corrected for single event upsets. Orbit choice matters too. Some mission profiles avoid the worst parts of the Van Allen belts. Others accept higher radiation in exchange for coverage and build more robust hardware to cope. Solar panels can be oversized and designed with degradation in mind, so the satellite still has enough power even after a big storm chews on them. Then there's the operational layer. Satellite operators maintain playbooks for space weather alerts. When a severe storm is forecast, they can delay delicate maneuvers, postpone software uploads, power down non-essential instruments, or change pointing modes to reduce drag or charging effects. For mega constellations in low Earth orbit, tracking and collision avoidance rules can be tightened temporarily because atmospheric drag becomes unpredictable. None of this makes satellites invulnerable. Big storms will still cause anomalies, reboot events, even permanent failures. But instead of losing an entire constellation, you might only lose a percentage. Instead of a GPS system collapsing globally, you might have degraded accuracy with graceful recovery over hours to days. The pattern is the same: layered defences, partial wins, no guarantees. And then we hit the part that doesn't fit neatly into engineering diagrams: policy and coordination. Power grids are often run by private or semi-private utilities, each with its own budget, regulators, and risk appetite. Space weather, meanwhile, doesn't respect borders or balance sheets. One CME hits everyone facing the sun, creating shared standards for how much Geiger transformer should tolerate, which lines get blocking devices. What minimum level of spare capacity is acceptable means negotiating between companies that compete with each other and regulators who may see storms as low-probability distractions compared to everyday reliability issues. On a national level, countries differ wildly. Some have centralised grid planning, others are patchworks of independent operators. Some invest heavily in space weather forecasting, others barely fund a data feed. International bodies can issue guidelines, but they can't make a utility in one country spend money to protect neighbours across the border from cascading outages. Even when everyone agrees storms are a problem, the trade-offs are messy. Hardening costs money. So does building new lines, integrating renewables, replacing aging infrastructure, and keeping electricity affordable. If you're a regulator, how much extra rate increase do you justify for protection against a once-in-a-century event that might or might not be as bad as the worst models? Over Harden, and you get accusations of overbuilding for sci-fi disasters while people struggle with bills. Under Harden. And you gamble that your luck will hold. There's also genuine uncertainty about the true upper bound. We've only observed the sun with modern instruments for a few decades. We know Carrington-class events are possible, and we've seen strong storms in 1921, 1989, 2003. But was 1859 near the worst the sun can do, or just a preview? The error bars are big, and that makes cost-benefit math fuzzy. So instead of a clean yes, we can harden the world, we get something more complicated. We can make blackouts shorter and less widespread. We can make satellite constellations more graceful under stress. We can coordinate grid operations so that when warnings come, people know exactly which levers to pull. We can't buy perfect safety. We can only buy resilience. Which brings this down from the level of grid operators and satellite designers to something more personal. If the big one does hit, and the professionals have done what they can, what does it look like on the ground? How do you, your family, and your community ride out a few days or weeks of a world that's temporarily less electrified than you're used to? Think of this less like prepping for the end of the world, and more like what our ancestors were already very, very good at, getting through a rough patch with the tools and people they have. A severe geomagnetic storm is essentially a fancy kind of blackout generator. The specifics why the transformers are mad, why the satellites are glitching, matter to engineers. For everyone else, the immediate experience is simple. The lights don't work, the card readers don't beep, your phone is suddenly a very expensive flashlight. So the question becomes, if the power went out across a big region, maybe for days, maybe in patches for weeks, how annoying does that get for you? And how do you turn disaster back into inconvenience? Start with the basics your great-grandparents would recognize. Water. If you live in a city or suburb, running water depends on pumps, which depend on electricity. Having a few days of drinking water at home, jugs, bottled water, even cleaned and filled containers is low-drama insurance. A common rule of thumb is about 4 litres, or a gallon, per person, per day. You don't have to become a bunker dragon guarding a cistern. A couple of cases in a closet is already a big upgrade from nothing. Food. You're not trying to feed a fortress for a year. You're trying to bridge a gap until supply chains and power stabilise. Shelf-stable stuff you actually eat: rice, pasta, canned beans, canned meat or fish, peanut butter, nuts, instant oats, plus whatever spices make you not hate life. Rotate it into your normal meals so it doesn't just sit there as a museum to your anxiety. Light and power. Flashlights that don't rely on your phone battery. Headlamps are weirdly life-changing when you need your hands. A small stash of batteries, maybe a couple of USB power banks charged and ready. If you live somewhere with frequent outages anyway, a small solar panel or a modest generator can move you from sitting in the dark to I can run the fridge for a few hours and keep phones alive. Cash. If payment networks are down, your card is just a shiny rectangle. A small amount of physical cash in small bills lets you buy essentials from places that can still function without their usual tech. Local markets, gas stations running on backup, that kind of thing. Medications, this one is boring until it isn't. If you rely on a prescription you truly cannot miss, building a small buffer, an extra week or month where legally possible, is one of the highest value preparations you can make for any disruption, solar storm or otherwise. And then there's the thing almost nobody thinks about until too late: how you're going to talk to people when the usual channels are unreliable. Cell networks can get overloaded even when they're working technically fine. Internet routing can be flaky. Have a simple communications plan with the people who matter to you. If something big happens and we can't reach each other, we'll try at these times on these apps. And if that fails, we meet here. Write it down. If there's an older relative who doesn't do group chats, make sure they know the plan too. Now zoom out from the front door. No matter how well stocked your pantry is, you're not an island. Communities are why our species made it through ice ages and volcanic winters. The same logic applies here. Who around you is going to need help in a prolonged power or communications disruption? Elderly neighbours, people with mobility issues, parents solo managing young kids, folks dependent on powered medical devices. Simply knowing who they are and having a loose agreement. If the power's out and things look weird, we check on each other, is a kind of social infrastructure. Local coordination doesn't have to mean building a bunker commune. It can be a street WhatsApp group, a tenant's email list, a neighbourhood association that has actually thought about where people would go if a building loses power and heat in winter. Backup power at the community level is where a solar storm intersects with politics and policy. Schools, community centres, libraries, fire stations, clinics, places people already gather are natural candidates for generators or solar plus battery systems sized not to make everything normal, but to keep refrigeration for medicines going, charge devices, run lights, maybe power fans or heating. Some cities are already creating resilience hubs like this. They help for heat waves, hurricanes, and yes, geomagnetic tantrums. All of this only works if people have some idea what's actually going on. During big space weather events, authoritative information typically comes from space weather agencies and grid operators. Storm level X. Expect radio outages, possible voltage control issues. We're doing Y and Z. Emergency management officers echo and interpret that. But information has its own version of GICs, slow, weird surges that get into every channel. In a blackout, your usual fact-checking habits get stress-tested. Screenshots of old headlines get recycled as if they're happening now. Someone hears transformer damage and turns it into months-long nationwide collapse in 3 retellings. People share dramatic claims because they're scared, bored, or trying to be helpful. So, before anything happens, figure out what your trusted sources are. National weather and emergency agencies, official utility accounts, a couple of reputable news outlets, maybe a local amateur radio group that relays official bulletins when the internet is spotty. Bookmark them, follow them, learn what their alerts look like. And during an outage, Treat viral rumours the way an electrician treats a live wire. Assume it's dangerous until proven otherwise. Ask, who's saying this? Can I find the same claim from an actual emergency agency or operator? Does the timeline even make sense? If someone says the grid is down for 6 months, 3 hours into an event, that's not a forecast. That's a fantasy. Underneath all of this is a kind of measured realism. Solar storms are not binary, harmless or civilization ending. They're a spectrum, and where a particular event falls on that spectrum interacts with how well we've maintained our infrastructure, how seriously operators take forecasts, what season it is, how hot or cold, how interconnected or brittle our systems are. The same storm that causes a few annoying GPS glitches and minor voltage issues in one decade could have been much more painful if it had hit a differently configured grid or a world less prepared. The same CME hitting Earth and missing major satellite constellations by a few years either way tells a different story. Preparedness at the personal and community level doesn't mean living in fear of the sun. It means accepting that we live inside a giant, occasionally temperamental magnetic bubble, that our technologies ride on top of that bubble, and that every so often it will wobble harder than usual. If you have some water, some food, some light, your meds, a way to charge a phone, a bit of cash, a plan to reach your people, and a habit of checking real information instead of the loudest rumour, you are already far ahead of where most humans found themselves in 1859. And that sets the stage for the most revealing question of all. If a Carrington-class storm did strike tomorrow, with everything we've built and everything we've learned, what would those hours and days actually look like? Picture this. It's a quiet Tuesday, somewhere on the sun, a magnetic field that's been twisting and knotting for days finally snaps. A flare erupts. X-rays and extreme ultraviolet light reach Earth in 8 minutes. If you were outside, you wouldn't notice a thing. But in those 8 minutes, high-frequency radio over the sunlit side of Earth starts to get noisy. Pilots, ship captains, ham radio operators hear the static first. Then the space weather centers light up. X-class flare. Big one. Coronal mass ejection likely. Over the next hour, solar telescopes and coronagraphs track the expanding cloud. Analysts start running models. Is it aimed at us, or just a near miss? The first reports say what you always hope to hear. Glancing blow, probably. Then the data firms up. The CME is coming straight at us. Fast. Now the clock is ticking. If it's only a strong storm, you might get 1836 hours warning. If it's Carrington fast, maybe 15. Space weather agencies issue alerts. Grid operators go into storm mode. They rebalance flows, bring more reactive power online, prepare to shed load if the system starts to wobble. Satellite operators tweak orientations, switch off non-essential systems, brace for radiation and drag. Airlines reroute polar flights, add extra fuel for longer paths. Most people, they see a couple of headlines, a push notification if they've installed a space weather app, and a friend posting sick auroras tonight on social media. Then they go back to whatever they were doing. Then the CME hits. The magnetosphere compresses. Currents begin flowing through the upper atmosphere. Long conductors on the ground, power lines, pipelines, undersea cables start picking up slow, deceptive surges. High latitudes feel it first. Control rooms in Canada, Scandinavia, northern Russia watch their meters go weird. In the likely scenario, operators see rising geomagnetically induced currents, tap their playbook, and the system rides it out unevenly. Some transformers overheat and trip. A few transmission corridors go offline. You get scattered outages, more in some places than others. Satellites lose some, but not all of their capacity. GPS a bit less accurate, some comms degraded, a few units possibly knocked out for good. Airlines deal with radio blackouts at certain frequencies, delay or reroute more flights. Internet routing gets messy but not dead. Packets find other paths. In the worst case scenario, the same initial physics looks similar until it doesn't. Local geology funnels more current into certain regions. A country with long east-west transmission lines built on highly conductive rock takes a bigger hit than its neighbour. Old, heavily loaded transformers in one grid fail in clusters before operators can shed enough load. Cascading blackouts leapfrog across multiple regions. Some big transformers aren't just tripped, they're damaged. And those are not overnight replacements. That's the knife edge. Same sun, same storm, different outcomes driven by details. Rock type, transmission layout, how much spare capacity the grid had that day, whether an operator believed the space weather forecast enough to take preemptive measures that cost real money. Latitude matters too. Near the equator you probably see incredible auroras and fewer grid issues. In mid-latitudes, impacts depend heavily on network design and grounding. In the far north, even a moderate storm can be dramatic. A Carrington-class one could push systems to places we've never actually tested in real life. Now zoom out from the grid to the society hanging off it. If large regions lose power for hours, it's a headache. Traffic lights out. ATMs and card readers down. Perishable food taking a hit. If those outages stretch into days in some pockets, you start to feel the invisible dependencies. Water treatment plants on backup generators burning fuel that has to be delivered by trucks that need functioning payment and scheduling systems. Fuel depots and pipelines whose pumps run on the same grid that's struggling. Hospitals juggling life support equipment against limited diesel, calling suppliers who are also operating in the dark. Supply chains don't fail all at once. They fray. A few factories halt because of power or communications. Parts don't ship. Other factories a continent away find themselves short next week. Refrigerated warehouses lose stock. Pharmacies see gaps in deliveries. The economy doesn't collapse, it limps, then lurches, then reroutes depending on how fast power, satellites and data links recover. And layered on top of that, the human response. Rumours running faster than electrons. Some people panic buy, others self-organise, set up charging stations, cook communal meals from thawing freezers, check on the vulnerable. The storm is the spark. Our systems and choices determine what burns and what just gets singed. If thinking in timelines and uncertainties like this interests you, how we reconstruct past disasters, what might be lurking in our future, there's a deeper dive waiting. I've put together a book on 12 of the strangest unexplained mysteries in science and history, from cosmic oddities to archaeological puzzles. It's on the website, discounted for this week only, and the link is in the description if you want to go down that rabbit hole after this. Because with solar storms, as with most of those mysteries, we're living in the grey zone between what we know, what we can model, and what we're going to find out the hard way the next time the sun really decides to remind us who's in charge. So let's bring it back to the night in 1859 when the sky caught fire. What do we actually know the Carrington event did? We know the auroras were obscene. Blood red, green and purple curtains blazing over Cuba, Rome, Hawaii. People thought cities were on fire. In some places you could read a newspaper at midnight. We know it drove electric currents into the ground and into anything long and conductive. Telegraph lines sparked, operators got shocked. In a few offices, batteries were disconnected, and the system kept running, powered only by the storm itself. Some equipment burned out. A lot of it just behaved weirdly for a few nights, and then went back to normal. We do not have evidence that it melted rails, set continents ablaze, or took down all technology of the 19th century. The world noticed, wrote about it, and moved on. But that's exactly why it matters. Because 1859 is a clean experiment, a truly extreme space weather event hitting a world whose only real vulnerability was miles of copper wire and a handful of primitive generators. Even then, the sun reached into our systems and started writing its own messages. Fast forward 160 plus years, we've taken those wires and built a global nervous system out of them. High voltage grids spanning continents, giant transformers delicately balanced near their limits, satellites wrapped around the planet like a metal halo, GPS timing sitting quietly at the heart of finance, logistics and communications, undersea cables carrying almost everything you're hearing right now. Same physics, much thicker web. That's the real lesson of 1859. Not that a solar storm will end the modern world, and not that it was fine back then, so it'll be fine now. It's that extreme space weather is real. It happens on human timescales, and what it does to us depends less on the storm and more on the systems we've built and the choices we make before it arrives. There is no fate here, only scenarios. In some of those futures, a Carrington-class event looks like a spectacular light show, noisy radios, a rough week for grid operators and satellite controllers, and a lot of annoyed passengers in airport lounges. In others, the same incoming cloud of plasma hits a world that underinvested in transformers, ignored forecasts, ran its infrastructure right up against the red line, and treated rare as never. That world hurts much more and for much longer. So what are the levers we actually control? Forecasting. The better we can watch the sun and model the magnetosphere, the more hours of warning we get. Hours matter. They tell grid operators when to lower loads, when to reconfigure networks, when to accept short-term pain to dodge long-term damage. Grid procedures playbooks that say, when you see this kind of alert, do this, even if it costs money today. Agreements between neighbouring regions to shed load, share capacity, and recover together instead of failing separately. Hardware hardening, better grounding, series capacitors and blocking devices that stop the slow, destructive currents from flowing into transformers. More spares, more redundancy, designing new equipment with storms in mind instead of as an afterthought. And then there's the quiet lever, individual and community resilience. No one can prep their way out of a global geomagnetic storm, but you can absolutely turn a bad week into a survivable inconvenience. A little food and water at home, a way to charge devices off-grid, printed copies of critical information, local networks, neighbours, community groups, radio clubs that can share resources and news when the digital layer gets noisy. You don't control the sun. You do control whether you're meeting the next big storm with empty shelves and zero plan, or with a bit of margin in your life and in your systems. If you want to explore more stories like this, the bizarre edge cases where geology, astronomy and deep time collide with human history, I've put together a book on 12 prehistoric secrets that almost broke our species. It dives into ancient bottlenecks, lost climates, and the strange paths that led to us. It's available through the website, and there's a link in the description if you want to keep going down that rabbit hole. Now I want to hear from you. Where are you listening from? And how do you think a big solar storm would play out where you live? Are you in high latitudes under the auroral oval, or closer to the equator watching from the sidelines? Drop your location and your thoughts in the comments. I read as many as I can, and they help shape what we cover next. If you found this interesting, or if it nudged you to see the sun and our technology in a slightly different way, tap like so more people actually get recommended this. Subscribe if you want more deep dives into the fragile edges of our civilization, and hit the bell if you'd like to know when the next one drops. The Carrington event was a warning shot we survived almost by accident. The next one will not be a surprise. What happens then is up to us.